Hello there and welcome to Life Beyond Scene, where we slow down, sit quietly with the world's most overlooked corners and try to understand what they are actually made of. Imagine a scar, not a dramatic one, not the kind that announces itself loudly, just a long, quiet scar running across the floor of the ocean, thousands of meters below the surface, in a part of the world where the weather is almost always bad and the ships that pass overhead are mostly just trying to get somewhere else. It has been there for roughly 50 million years. It stretches for more than 3,000 kilometers. And despite being one of the longest oceanic trenches on this entire planet, most people have never heard of it, and most scientists have never directly looked at the bottom of it. Tonight we are going to talk about the Aleutian Trench, not the Mariana Trench, which gets all the documentaries and the record-breaking dives and the famous names attached to it. Not the Tonga Trench or the Kermadec, which have both received serious modern scientific attention in recent years. The Aleutian Trench, the long, cold, seismically violent, sediment-buried, storm-surrounded place that runs along the southern edge of the Aleutian Island chain from the coast of Alaska curving westward toward the Kamchatka Peninsula in the Russian Far East, reaching its deepest point at around 7,679 meters near Attu Island, which is itself one of the most remote pieces of land in the United States. Before we go any further, I want to ask you something simple. Where are you right now? Are you somewhere warm, maybe in bed with the lights already off? Is it late where you are, or are you listening in the early hours of the morning when the world outside is quiet and the darkness feels a little more like the ocean than usual? Maybe you are somewhere cold, and that actually makes a strange kind of sense tonight. Whatever the answer is, I am glad you are here. And if you find yourself settling in and enjoying this kind of quiet, careful storytelling, it would mean a lot if you took a moment to like this video and subscribe to the channel. It helps more than you might think, and it lets us keep making these long, slow explorations of places and questions that deserve more attention than they usually get. Now, back to the trench. The Aleutian Trench does not have a famous story attached to it. There is no James Cameron dive, no breathless press release from a record-breaking submersible, no viral photograph of something strange and bioluminescent hovering at the bottom. What it has instead is a kind of enormous, patient obscurity. It sits there, running its full 3,400 kilometers through some of the roughest ocean on Earth, and the scientific community has, for reasons that turn out to be quite specific and quite interesting, largely left it alone. That fact alone is worth sitting with for a moment. We live in an era when deep-sea exploration has genuinely accelerated. The tools are better than they have ever been. There are full ocean-depth vehicles that can reach the absolute bottom of any trench on Earth. There are autonomous landers that can be dropped from a ship and left to sink to the Hadal zone, collect samples, and float back to the surface on their own. There are high-definition cameras that can operate under pressures that would crush a car into a rough cube of metal in seconds, and yet the deepest parts of the Aleutian Trench remain, as of the early 2020s, almost entirely unvisited by modern scientific equipment. No publicly available ROV footage exists of the Hadal zone down there. The most recent biological sampling from the deeper sections was done by Soviet research vessels in the 1950s and 1960s. That is not a typo. The most recent comprehensive biological work from the deepest part of this trench is older than the Apollo program. So the question we're going to spend tonight with is not a dramatic one, and it is not a mystery in the thriller novel sense. It is more practical than that, and in some ways more interesting because of it. Why, after decades of improving technology and genuine scientific interest in the Hadal zone, do researchers still largely avoid the deepest parts of the Aleutian Trench? What is actually keeping them away? The answer, it turns out, is not one thing. It is a combination of geology, weather, engineering, money, institutional habit, and a set of very specific physical conditions that make this particular trench significantly harder to work in than the ones that tend to get all the attention. Each of those factors is worth understanding on its own, and together they paint a picture of a place that is not just deep, but deeply inconvenient in almost every direction you approach it from. Let's start with the geography, because it matters more than it might seem at first. The Aleutian Trench follows the arc of the Aleutian Islands, which themselves curve in a long, sweeping chain from the Alaska Peninsula westward across the North Pacific. The islands are volcanic, windswept, and largely uninhabited. The largest settlement along the chain is Dutch Harbour on Unalaska Island, which most people in the continental United States probably know, if they know it at all, from the television series about crab fishing. It is a real place, genuinely remote, with a population of around 4,000 people, and an economy built mostly around commercial fishing and the logistics of getting things to and from the outer islands. It is also the closest thing to a major port that researchers working on the Aleutian Trench have access to, and by the standards of deep-sea research infrastructure, it is quite limited. The trench itself runs parallel to the island chain, sitting on the ocean-facing southern side. At its shallowest, it is still several thousand meters deep. At its deepest, near Attu Island, at the far western end of the chain, it reaches that figure of 7,679 meters. To give that some scale, if you dropped Mount Rainier into the deepest part of the Aleutian Trench, the summit would still be more than 3 kilometers underwater. The trench is not just deep in an abstract sense. It is deep in a way that requires specialized equipment just to reach, let alone to study. And yet, compared to the Mariana Trench, which reaches a maximum depth of around 10,900 meters and has been visited dozens of times by crewed and uncrewed vehicles, the Aleutian Trench is practically invisible in the scientific literature when it comes to adalt biology and direct geological observation of the trench floor. The Mariana has its own dedicated research programs, its own famous landmarks like the Challenger Deep, its own Wikipedia rabbit holes that go on for hours. The Aleutian has mostly silence. Part of that difference comes down to location. The Mariana Trench sits in the Western Pacific, in a region of ocean that is, by the standards of deep-sea research, relatively accessible. The weather there can be rough, but it is not consistently brutal. There are established research ports in Guam and Japan with the infrastructure to support major oceanographic expeditions. The Aleutian Trench, by contrast, sits in one of the most consistently hostile stretches of ocean on the planet. The North Pacific along the Aleutian chain is famous among mariners for a reason. Storms roll through there with a kind of regularity and intensity that makes long-duration scientific operations genuinely difficult to plan around, and genuinely dangerous when the weather turns faster than expected. But location and weather alone do not fully explain the gap. The Kermadec Trench, which sits northeast of New Zealand and reaches depths of over 10,000 meters, is also fairly remote. The Tonga Trench is not exactly next door to a major research university. Both of those trenches have received serious targeted scientific attention in recent years, including modern ROV dives and biological sampling programs. The Aleutian has not. So there is something more specific going on, something that comes from the particular combination of this trench's geology, its seismic activity, its sediment conditions, and the very particular set of engineering challenges that its depth and environment create. We will get into all of that, but it helps to first have a clear picture of what the Aleutian Trench actually is, in a physical sense, before we start talking about why it is so hard to study. One thing that is easy to underestimate when you're looking at a map and the trench appears as a thin blue line along the bottom of the Aleutian chain is just how long it is, 3,400 kilometers. To put that in more familiar terms, that is roughly the distance from New York City to Los Angeles, and then another few hundred kilometers beyond that. If you drove along the length of the Aleutian Trench at highway speed, it would take you over 30 hours without stopping. It is one of the longest oceanic trenches in the world, longer than the Peru-Chile Trench, longer than the Tonga-Kermadec system if you measure them separately, comparable in length only to a handful of the planet's most significant geological features. And along that entire length, the deepest sections, the Hadal zone below 6,000 meters, have been directly sampled almost not at all by modern science. That is the gap we are sitting with tonight. It is also worth noting, before we move further into the story, that the Aleutian Trench is not just a curiosity for biologists and geologists. It is directly relevant to the safety of millions of people who live around the Pacific Rim. The subduction zone that created the trench is one of the most seismically active in the world. The earthquakes it produces have, historically, generated tsunamis that have crossed the entire Pacific Ocean and killed people as far away as Hawaii and Japan. Understanding what is happening in and around this trench is not just an academic question. It has real, practical stakes. But the science of the trench floor itself, the direct observation and sampling of what is actually down there, lags far behind what you might expect given those stakes. And that gap between what we know we should understand and what we have actually managed to find out is where tonight's story lives. There is something quietly striking about that. Here is a feature of the Earth's surface that is thousands of kilometers long, thousands of meters deep, sitting beneath one of the most seismically important subduction zones on the planet. And the most detailed biological picture we have of its deepest parts comes from Soviet research ships that were out there when Nikita Khrushchev was still in power. The world has changed enormously since then. The technology has changed. The scientific questions have changed. But the trench has mostly just continued being there, doing what it has always done while the expeditions went elsewhere. What makes this interesting, and I think genuinely worth spending a long evening thinking about, is that the reasons for this neglect are not mysterious or hidden. They are practical, specific, and in some cases quite surprising. They involve the behaviour of ocean weather systems and the tensile strength of steel cables, and the way scientific funding tends to flow toward places that already have data. They involve the history of a particular research vehicle that was lost at depth in a different trench, and what that loss did to the institutional appetite for risk. They involve the thickness of sediment layers and the chemistry of deep water pressure, and the logistical reality of operating a research ship in a place where the nearest decent harbour is itself in the middle of nowhere. All of that is worth understanding slowly, piece by piece, because each piece adds something to the picture of a place that most of the world has simply never thought about. So let us begin at the beginning, with the forces that actually created the Aleutian Trench in the first place, because you cannot really understand why this place is so difficult to work in until you understand what kind of geological event built it, and what that event is still doing right now, beneath the cold water. The Pacific Ocean floor is not still. That is one of those facts that is easy to accept intellectually and almost impossible to really feel in your body, because the timescales involved are so far outside ordinary human experience that they resist imagination. But the Aleutian Trench exists precisely because the ocean floor is moving, has been moving for tens of millions of years, and continues to move right now, tonight, while you are listening to this. The trench is not a passive feature of the Earth's surface, it is an active one. It is the visible expression of a collision that has been happening in slow motion for longer than most of the major mountain ranges on land have existed. The mechanism behind it is called subduction, and it is worth spending a few minutes with, because it is the foundation of almost everything else that makes the Aleutian Trench what it is. The Pacific Plate, which is the largest tectonic plate on Earth, covering roughly 103 million square kilometres of ocean floor, is moving. It moves northwest at approximately 7 centimetres per year. That sounds small, and in any given year it is. 7 centimetres is about the length of a finger, but over millions of years, 7 centimetres per year becomes hundreds of kilometres of movement, and that movement has consequences. When the Pacific Plate reaches the edge of the North American Plate along the southern margin of the Aleutian Island chain, it does not simply stop. It cannot stop. The two plates are both enormous, both under enormous pressure from the forces driving them, and there is nowhere for all of that mass and momentum to go except downward. The Pacific Plate bends and dives beneath the North American Plate, angling down into the Earth's mantle at a relatively shallow dip of somewhere around 20 to 30 degrees in most parts of the Aleutian system. That downward bending edge of the Pacific Plate is where the trench is. The trench is, in the simplest physical terms, the place where the ocean floor folds under. If you could stand at the bottom of the Aleutian Trench and look around, you would be standing on the surface of the Pacific Plate itself, at the point where it begins its long descent into the interior of the Earth. The water above you would be somewhere between 6 and 7.5 kilometers deep, depending on exactly where along the trench you are standing. The walls around you would be steep, particularly on the inner wall, which is the wall on the North American plate side. That inner wall rises sharply, shaped by the compression and deformation of the overriding plate as the Pacific Plate grinds beneath it. The outer wall, the Pacific Plate side, has a gentler slope in places, though it is interrupted by faults and scarps created by the bending of the plate as it curves downward. This geometry matters for understanding the trench as a physical space, because it is not simply a uniform slot in the ocean floor. It is an asymmetric structure. The two walls behave differently, are made of different materials, and are subject to different stresses. The inner wall on the North American side is built largely from the deformed and compressed sediments and rocks of the continental margin, scraped off the descending Pacific Plate and piled up in what geologists call an accretionary wedge. The outer wall is the bending edge of the oceanic plate itself, and it has a different texture and a different relationship to the seismic activity that runs through the whole system. When you read descriptions of the trench in geological literature, this asymmetry comes up again and again as a complicating factor, because it means that the two sides of the trench are not simply mirror images of each other. They are geologically distinct environments that happen to be a few kilometers apart horizontally and thousands of meters apart vertically. The trench itself is thought to have begun forming around 50 million years ago, during the Eocene epoch. At that point in Earth's history, the Aleutian subduction zone was getting started as the Pacific Plate's motion brought it into sustained contact with the North American plate along this particular boundary. 50 million years is long enough for the trench to have reached its current dimensions, long enough for the Aleutian Island arc to have been built up by the volcanic activity that subduction produces, and long enough for enormous quantities of sediment to have accumulated in and around the trench. The islands themselves, those long strings of volcanic peaks stretching from the Alaska Peninsula out toward Kamchatka, are directly connected to what is happening in the trench. As the Pacific Plate descends into the mantle, it releases water and other volatiles into the mantle rock above it, which lowers the melting point of that rock and produces magma. That magma rises, and where it reaches the surface, you get volcanoes. The Aleutian Islands are the surface expression of that process, a chain of volcanic peaks that has been built and rebuilt over tens of millions of years by the same subduction that carved the trench below. It is a striking thing to think about, that the islands and the trench are products of the same event, just expressed differently. The trench is the wound, and the islands are the scar tissue. Or maybe it is the other way around. Either way, they are inseparable. Now, the Hadal zone. This is the term used for the deepest parts of the ocean, specifically the regions below 6,000 meters. The word comes from Hades, the Greek underworld, and whoever coined it was not being overly dramatic. Below 6,000 meters, the conditions are genuinely extreme in ways that go beyond simply being very deep. The pressure at 6,000 meters is already around 600 atmospheres, meaning 600 times the pressure you feel sitting at sea level. At the deepest point of the Aleutian Trench, near Attu Island, where the depth reaches approximately 7,679 meters, the pressure is closer to 770 atmospheres. That is roughly 11,300 pounds per square inch. To put that in terms that are a little easier to hold in your mind, it is about the equivalent of having 55 fully loaded Boeing 737 aircraft stacked on top of a single square inch of surface. Everything that goes down to those depths has to be designed to withstand that pressure without deforming, cracking, imploding, or failing in any of the other creative ways that pressure finds to destroy things that were not built for it. The Hadal zone in the Aleutian Trench begins somewhere around 6,000 meters and extends to that maximum depth near Attu. That is a vertical range of roughly 1,700 metres of Hadal environment, which is substantial. Not every part of the trench floor sits in the Hadal zone. The trench has shallower sections, areas where the depth is 4,000 or 5,000 metres rather than 7. But the deeper sections, the parts that are hardest to reach and least studied, fall squarely in Hadal territory, and those are the parts that this story is really about. One of the things that makes the Aleutian Trench structurally distinct from some other well-studied trenches is the sediment. The trench sits close to the Alaskan continental margin, which is an enormous source of sediment. Rivers draining the Alaska Range carry glacial sediment into the Gulf of Alaska. Coastal erosion along the Aleutian Islands contributes material. The continental shelf to the north sheds sediment downslope. All of this material finds its way, eventually, into the trench. In some parts of the Aleutian Trench, the sediment layer on the floor is extraordinarily thick, exceeding 3 kilometres in places. 3 kilometres of accumulated mud, sand, organic material, and volcanic ash sitting on top of whatever the actual basaltic ocean floor looks like beneath it. That is a significant amount of material, and it has accumulated there because the trench acts as a kind of sediment trap, a long narrow basin that catches everything flowing off the continent to the north and the plate to the south. For comparison, the Mariana Trench, which is the most studied deep trench in the world and sits far from any major continental sediment source, has a relatively thin sediment layer on its floor. In some parts of the Mariana, you can sample the underlying rock without going through enormous thicknesses of overlying sediment. In the Aleutian Trench, you're dealing with kilometres of sediment before you even get close to the geological basement. This creates a very different kind of research environment. Sediment cores from the Aleutian Trench can be scientifically valuable, and some have been taken, but they tell a complicated story that takes considerable effort to interpret, because you are reading through layers that represent millions of years of accumulation, including multiple episodes of turbidite deposition. Turbidites are worth explaining here, because they are one of the more dramatic features of the Aleutian Trench floor, and they are directly connected to the seismic activity of the subduction zone. A turbidite is a deposit left by a turbidity current, which is essentially an underwater avalanche of sediment. When an earthquake strikes the subduction zone, which happens with remarkable frequency in the Aleutian system, it can destabilize sediment that has been accumulating on the slopes of the trench walls. That sediment, sometimes enormous quantities of it, flows rapidly down the slope and across the trench floor, depositing a layer of material that is distinctly different in texture and composition from the sediment that accumulates slowly through normal particle settling. These turbidite layers are visible in sediment cores as discrete bands, and they serve as a kind of geological record of past earthquakes. But they also mean that the trench floor is not a stable, undisturbed environment. It is a place that periodically gets buried under flows of sediment triggered by the same seismic activity that makes the region so geologically active. For anything living on the trench floor, this is a significant fact. The fauna of Hadal trenches are adapted to extreme pressure and cold temperatures and low food availability, but they are also, in trenches like the Aleutian, adapted to an environment that can change rapidly and dramatically when a major earthquake sends a turbidity current across the floor. Whether that disruption kills the organisms living there or simply displaces them temporarily, or whether the organisms have developed behavioural or physiological strategies for dealing with it, is one of the many things we do not know, because we have not been down there to look. The subduction geometry also means that the trench is not a geologically quiet place in the intervals between major earthquakes. The Pacific plate is continuously moving, continuously grinding against and beneath the North American plate, and that continuous motion produces a background level of seismic activity that is, by the standards of most places on Earth, quite high. Small earthquakes, magnitude 2 and 3 events, occur in the Aleutian subduction zone with a regularity that would be alarming anywhere else, but is simply the normal condition of this particular piece of the planet. The trench floor sits at the centre of this activity. It is not a place of geological rest. It is a place of geological work, ongoing, relentless, and expressed in the slow accumulation of sediment and the occasional violent redistribution of everything that has been carefully deposited. There is something almost paradoxical about the relationship between the forces that created the trench and the forces that make it so hard to study. The same subduction that built this enormous deep feature of the ocean floor also generates the seismic activity that destabilizes equipment, that creates the tsunami risk that makes the region scientifically important, and that produces the sediment conditions that complicate sampling and interpretation. The trench is a product of its own difficulty. It is deep because of the subduction, and it is hard to work in because of the subduction, and it is scientifically important because of the subduction. All of those things come from the same source, the same slow, powerful, continuous process that has been running for 50 million years and shows no sign of stopping. What this means, practically, is that any scientific expedition hoping to work in the deep Aleutian Trench is not simply dealing with depth as an engineering challenge. It is dealing with depth plus seismic instability, plus sediment complexity, plus the particular geological character of a subduction zone trench, which is structurally and chemically different from the mid-ocean trench environments that some of the most famous deep-sea research has taken place in. The Aleutian Trench is its own kind of place. It shares some characteristics with other Hadal environments, but the specific combination of its geology, its sediment, its seismicity, and its location makes it something that cannot simply be approached with the same toolkit and the same assumptions that work elsewhere. That specificity is part of what makes it interesting, and it is also part of what makes it so persistently underexplored. Because the scientific and engineering challenges here are not generic deep-sea challenges. They are Aleutian Trench challenges particular to this place, requiring particular solutions, and those solutions have not yet been fully developed or deployed. The trench has been waiting, in its cold and pressurized darkness, for someone to figure out how to approach it properly. But before we get into the full picture of those challenges, it is worth spending some time with a history of what this subduction zone has already done in recorded human history to make its presence felt. Because the earthquakes and tsunamis associated with the Aleutian Trench are not abstract geological events, they are documented, specific, and in some cases catastrophic. An understanding that history is part of understanding why this trench matters, and why the gap between its importance and the attention it receives is so striking. The year 1946 is a reasonable place to start, because it is the moment when the Aleutian subduction zone made itself known to the wider world in a way that could not be ignored or explained away. On the 1st of April that year, at 4:28 in the morning local time, a magnitude 8.6 earthquake struck the seafloor south of Unimak Island, near the eastern end of the Aleutian chain. The earthquake itself was felt across a wide area, but the shaking was not the thing that people would remember. What followed the shaking was the thing that mattered. The tsunami generated by that earthquake travelled across the Pacific at the speed of a commercial jet aircraft, somewhere around 800 kilometers per hour in the open ocean, which sounds fast until you realise that the waves were so long and so low in the open sea that ships passing through them likely felt nothing at all. The energy was moving, but it was moving invisibly, stretched across hundreds of kilometres of water. It was only when that energy reached shallow coastlines and began to compress and rise that it became visible, and by then there was very little time to respond. The Scotch Cap Lighthouse on Unimak Island was one of the first structures in the direct path of the wave. It was a reinforced concrete building, not a flimsy structure, sitting on a bluff about 14 metres above sea level. 5 men were stationed there. The wave that struck Unimak Island was later estimated to have reached heights of between 20 and 30 metres in some locations, and the lighthouse was simply gone. All 5 men died. When rescue crews arrived, they found the concrete foundation scraped nearly clean. The wave had not just flooded the building, it had removed it. further across the Pacific in Hilo, Hawaii, the tsunami arrived with less height, but still enough force to cause serious damage. Hilo sits on a bay that naturally focuses and amplifies incoming wave energy, and the 1946 tsunami exploited that geography efficiently. The waves that struck Hilo reached about 8 meters in some areas and killed 96 people there. In total, the tsunami killed 159 people across the Pacific, making it one of the deadliest tsunamis in 20th century American history. It was the disaster that eventually prompted the creation of the Pacific Tsunami Warning System, which was established in 1949, 3 years after the event. What is worth understanding about the 1946 earthquake in the context of the Aleutian Trench is where it originated. The rupture occurred along the subduction interface, the boundary where the Pacific plate is sliding beneath the North American plate, which is precisely the tectonic structure that created the trench and continues to define it. The earthquake was not a coincidence of geography. It was a direct expression of the same forces that built the trench over 50 million years, the same slow collision that continues today at roughly 7 centimeters per year. The trench and the earthquakes are the same thing, viewed from different timescales. 11 years later, in 1957, the subduction zone produced another major event. The Aleutian Islands earthquake, which struck on March 9th of that year, registered a magnitude of 8.6, essentially equivalent in energy to the 1946 event. The epicenter was located near the Aleutian Islands group in the central Aleutians, and the rupture length was enormous, extending along the subduction interface for something in the range of 1,200 kilometers. That is a rupture stretching a distance roughly comparable to driving from New York City to Chicago. The earthquake generated a Pacific-wide tsunami that caused damage in Hawaii and along the coastlines of the western United States, though the death toll was lower than 1946 in part because warning systems were now in place. The tsunami still caused significant damage in Hilo, destroying buildings and injuring people, and it was observed across the Pacific from Japan to South America. 8 years after that, in 1965, the Rat Islands earthquake struck. Magnitude 8.7, centered near the Rat Islands group in the western Aleutians, it generated another tsunami that was observed across the Pacific. The pattern was becoming clear, even if the underlying mechanics were still being worked out by seismologists at the time. The Aleutian subduction zone was not a place that produced one great earthquake and then rested. It was a system capable of producing major ruptures repeatedly, in different segments, with intervals of years to decades between events in any given segment, but with the overall system remaining persistently active. And then there was 1964. The Good Friday earthquake, which struck on March 27th of that year, is worth discussing carefully because it sits at the edge of the Aleutian system in a way that requires some geographic nuance. The epicenter was near Prince William Sound in Alaska, which is east of the main Aleutian chain, and the earthquake is often described separately from the Aleutian Trench proper, but it belongs to the same subduction system. The Pacific Plate's descent beneath the North American plate does not stop neatly at the eastern end of the Aleutian Trench. The subduction zone continues eastward beneath the Gulf of Alaska and the Alaska Peninsula, and the 1964 earthquake was a rupture of that same convergent boundary, just in a different segment. The numbers associated with the Good Friday earthquake are still striking. Magnitude 9.2, making it the most powerful earthquake ever recorded in North America, and the second most powerful ever recorded anywhere on Earth, after the 1960 Valdivia earthquake in Chile. The rupture extended approximately 800 kilometers and lasted somewhere between 4 and 5 minutes, which is an extraordinarily long time for a seismic event. The ground in Anchorage dropped by as much as 2 meters in some areas and rose by as much as 11 meters in others. The tsunami that followed killed 139 people across Alaska, Oregon, and California, and was observed as far away as Antarctica. In the town of Valdez, Alaska, a submarine landslide triggered by the shaking generated a local wave that struck before the main tsunami arrived. In Chenega, a small Alaska native village, 23 of the 68 residents were killed. The reason to include the 1964 earthquake in a discussion of the Aleutian Trench, even though it is technically adjacent to rather than directly within the trench system, is that it illustrates the scale and character of the seismic environment that surrounds this place. The Aleutian subduction zone is not a background feature. It is one of the most seismically productive tectonic boundaries on Earth, and the trench is the surface expression of the collision that generates all of this activity. The earthquakes are not happening near the trench. They are happening because of the same process that created the trench, and they are happening along the same interface that defines its geology. For anyone thinking about sending scientific equipment to the bottom of the Aleutian Trench, this history is not abstract. It is operationally relevant. The trench floor is not a static environment waiting patiently to be sampled. It is the floor of an active subduction zone that has produced multiple magnitude 8+ earthquakes in the last 80 years, any one of which could trigger turbidity currents capable of burying or destroying equipment, could snap mooring cables, could destabilize the sediment surface that instruments are resting on. The risk is not hypothetical. It is documented, repeated, and geologically ongoing. There is also the matter of the lower level seismicity, the constant background noise of the subduction zone. Between the major events, the Aleutian system produces a steady stream of smaller earthquakes, magnitude 4 and 5 events that occur frequently enough to be almost unremarkable to the seismologists who monitor them. The National Earthquake Information Center records dozens of earthquakes in the Aleutian region every month. Some weeks, there are several notable events. This is not a system in a quiet interseismic period. It is a system that is continuously active, continuously releasing stress in small increments while also accumulating stress toward the next large rupture. For deep-sea equipment, even moderate seismic events can be problematic. A lander sitting on the trench floor at 7,000 meters depth is connected to the surface by an acoustic release mechanism, which allows it to drop its ballast weight and float back up when triggered by a sound signal from the ship. That system depends on the lander remaining upright, on the release mechanism functioning correctly, and on the acoustic signal travelling clearly through the water column. A seismic event that shifts the sediment surface, or that generates enough acoustic noise in the water column to interfere with the signal, or that triggers a small turbidity current that buries part of the lander, can complicate or prevent recovery. Losing a deep-sea lander is not just an expensive inconvenience. It represents the loss of whatever samples and data it was carrying, potentially months or years of planning and preparation. The 2021 Chignika earthquake, which struck on July 29th of that year with a magnitude of 8.2, is a useful recent reminder that the system remains capable of producing very large events. The epicenter was near the Alaska Peninsula, east of the main Aleutian chain, but again part of the same subduction system. It was the largest earthquake to strike the United States since the 1964 Good Friday event. A tsunami warning was issued, residents of coastal Alaska communities evacuated, and while the resulting tsunami was relatively modest, the event served as a clear demonstration that the seismic hazard along this subduction boundary is not a historical artifact. It is present, current, and ongoing. What the earthquake and tsunami history of the Aleutian system does, in the context of understanding the trench, is establish something important about the nature of the place. It is not simply deep. Plenty of deep places in the ocean are geologically quiet, sitting in old, cold, oceanic crust far from active plate boundaries, accumulating sediment slowly and peacefully. The Aleutian Trench is not that kind of place. It is deep and it is active, and the activity is not incidental to its depth. The depth and the activity come from the same source. The subduction that pulled the Pacific Plate down to create the trench is the same process that generates the earthquakes, the tsunamis, the turbidites, the sediment instability, and the continuous low-level seismicity that makes the region one of the most geologically energetic places on the planet. There is something almost clarifying about sitting with that fact for a moment. Scientists have not simply overlooked the Aleutian Trench the way you might overlook a quiet corner of a library. They are dealing with a place that actively resists easy study. The resistance is geological. It is built into the structure of the trench itself, into the physics of the subduction zone, into the history of events like Scotch Cap and Hilo and Prince William Sound. Every major earthquake along this system is a reminder that the trench is not waiting passively. It is part of a living, moving, occasionally violent geological process that has been running for 50 million years and will continue running long after any particular research expedition has come and gone. And yet, the scientific importance of understanding this trench has not diminished because of that difficulty. If anything, the seismic history makes understanding the trench more urgent. The geometry of the trench floor, the distribution of sediment, the structure of the subduction interface at depth. All of these things are directly relevant to understanding how future earthquakes in this system will behave, how large they might be, how much slip might occur on the fault, and therefore how large a tsunami they might generate. The trench is not just a biological and geological curiosity, it is a piece of critical infrastructure for understanding the hazard that the Aleutian subduction zone poses to millions of people living around the Pacific Rim. But understanding the seismic history of the region is only one part of the picture. Because even if you set aside the earthquake risk, even if you imagine a version of the Aleutian Trench that was geologically quiet and seismically calm, you would still be dealing with one of the most operationally challenging ocean environments on Earth, for reasons that have nothing to do with what is happening beneath the seafloor. The challenge above the surface is just as real, and in some ways just as daunting as the challenge below it. The weather in the Aleutian region is its own category of difficult, and it shapes every practical decision about what kind of science can be done here, and when and how. The Aleutian Islands sit at the top of the Pacific, strung out in a long westward arc between mainland Alaska and the Kamchatka Peninsula, and the stretch of open ocean surrounding them is, by most meteorological measures, one of the least hospitable places on the surface of the Earth to operate a research vessel. This is not an exaggeration made for atmosphere. It is a practical, documented reality that anyone who has spent time on a ship in the Bering Sea or the North Pacific near the Aleutian chain will confirm without hesitation. The weather here is not occasionally bad. It is structurally, persistently, seasonally difficult, shaped by a combination of geography, ocean temperature gradients, and atmospheric dynamics that conspire to produce conditions that would be considered extreme almost anywhere else in the world. The fundamental driver is the Aleutian Low, a semi-permanent area of low atmospheric pressure that sits over the North Pacific during the fall and winter months. It is one of the major centres of action in the Northern Hemisphere's atmospheric circulation, and it draws storm systems toward the Aleutian region the way a drain pulls water. Storms that develop over the open Pacific track northeast and intensify as they approach the island chain, and the relatively warm water of the Kuroshio Current mixing with cold Arctic air masses creates conditions for rapid cyclogenesis, which is the meteorological term for a storm deepening very quickly. In practical terms, this means that weather forecasts in the Aleutian region can become unreliable within 24 hours, and conditions that look manageable in the morning can deteriorate into something genuinely dangerous by afternoon. Average significant wave heights in the region during winter months frequently exceed 6 meters, and during major storm events, wave heights of 10 to 12 meters are not uncommon. Sustained wind speeds above 60 knots, which is roughly 70 miles per hour, occur regularly. These are not the kinds of numbers that make a research ship's captain comfortable, and they are not the kinds of conditions in which you lower sensitive scientific equipment over the side of a vessel on a cable. To put that in some context, the Beaufort scale classifies sustained winds above 64 knots as hurricane force. The Aleutian region experiences conditions approaching or reaching that threshold with a regularity that is, depending on your relationship to the ocean, either impressive or alarming. For a deep-sea expedition, surface conditions matter in ways that are not always obvious from the outside. When a research team deploys a free-falling lander, which is the kind of instrument most commonly used for hadal work, the lander is lowered over the side of the ship and then released to sink under its own weight, carrying cameras, traps and recording equipment down to the seafloor. The descent takes hours. At Aleutian Trench depths of around 7,600 metres, a lander travelling at roughly 1 metre per second will take more than 2 hours just to reach the bottom. During that time, and during the additional hours it spends on the seafloor, and during the hours it takes to ascend after releasing its ballast weight, the ship must remain in the general area, holding station or drifting carefully. In calm conditions this is manageable. In 6-metre swells with 60-knot winds, it becomes a serious operational problem, and in conditions beyond that it becomes impossible. The cable management issue alone is significant. Even landers that descend freely rather than on a tether require the ship to maintain a known position relative to the lander's expected location on the seafloor, so that the acoustic release signal can be sent from close enough to be received clearly. In rough weather, a ship can be pushed off position faster than its dynamic positioning system can compensate, especially in a vessel that is not purpose-built for station keeping in extreme conditions. And if the ship is using a tethered ROV rather than a free-falling lander, the problem compounds considerably. A tether connecting a vehicle at 7,000 metres to a ship on the surface is subject to enormous hydrodynamic forces in rough conditions. The cable can develop dangerous angles, create drag on the vehicle below, or in worse cases become entangled or snapped. The mechanics of managing a 7-kilometre cable in heavy weather are genuinely complex, and they require conditions that the Aleutian region simply does not reliably provide. Contrast this with the Mariana Trench, which sits in the western tropical Pacific, roughly between Guam and the northern Mariana Islands. The sea state in that region is, on average, substantially calmer. Typhoon season aside, the western tropical Pacific offers longer windows of workable conditions for deep-sea operations. Ships can hold station more reliably. Landers can be deployed and recovered with greater confidence. The logistical math is simply more favourable, and this is one of the reasons why the Mariana Trench has attracted repeated expeditions while the Aleutian Trench has not. The science is not necessarily more interesting at the Mariana. The conditions for doing the science are just more forgiving. The weather window for safe deep-sea operations in the Aleutian region is narrow. Most researchers who have worked in the area identify a period from roughly late June through early September as the most reliable for ship operations, and even within that window, conditions can change quickly and unpredictably. A 3-week research cruise, which is a typical duration for a deep-sea expedition, might realistically expect only a handful of days within that window where conditions are calm enough for full deep-sea lander or ROV operations. If the ship encounters a storm in the first week and loses several days, the entire scientific program can be compromised. Expeditions to calmer regions can often recover from weather delays by extending operations slightly or shifting to a different site. In the Aleutians, the margin for error is much smaller. There is also the matter of where the ship starts from and returns to. The nearest significant port infrastructure to the central and western Aleutian Trench is Dutch Harbour on Unalaska Island. Dutch Harbour is a real and functioning port, primarily known as one of the largest commercial fishing ports in the United States by volume. It has fuel, it has some repair capacity, and it has the kind of logistical infrastructure that keeps fishing fleets operating. What it does not have, in any substantial way, is the kind of deep-sea research infrastructure that major oceanographic expeditions typically rely on. There is no large oceanographic institution based there. There is no ready supply of specialised scientific equipment or technicians. If something breaks on a research cruise operating out of Dutch Harbour, the nearest major repair facility is likely in Seattle, which is roughly 2,400 kilometres away by sea. Getting replacement parts or additional personnel to the ship is not a quick or easy process. Compare this to the infrastructure available for expeditions to the Mariana Trench, which typically stage out of Guam. Guam has a substantial port a US Navy presence with associated technical resources and a much larger logistics network. It is also served by regular flights from major Pacific hubs, which makes moving personnel and equipment in and out considerably more practical. The logistical friction of operating from Dutch Harbour versus operating from Guam is real, and it accumulates across every phase of an expedition, from the initial transit to the final recovery of equipment. The transit itself is worth thinking about. A research vessel sailing from Seattle to the western Aleutian Trench, near Attu Island where the deepest depths are found, is looking at a journey of roughly 3,000 kilometres. That is several days of transit time each way, in waters that are themselves often rough, and that transit time comes directly out of the scientific programme. Ships cost money to operate, typically tens of thousands of dollars per day for a major research vessel, and every day spent in transit is a day not spent collecting data. Expeditions to more accessible trenches can dedicate a higher proportion of their ship time to actual science. The Aleutian Trench, sitting at the end of a long and difficult transit, starts every expedition at a disadvantage before the first instrument is even deployed. The practical effect of all this is that planning an Aleutian Trench expedition requires a kind of risk tolerance and logistical flexibility that is genuinely unusual, even by the standards of deep-sea research, which is itself an already demanding field. Program managers at funding agencies who review expedition proposals are not indifferent to these realities. When evaluating the scientific return per dollar spent, an expedition to a trench with a narrow weather window, limited port support, long transit times, and documented seismic risk will always face harder questions than an expedition to a calmer, better supported location. This is not a failure of scientific imagination. It is a rational response to real operational constraints. But the cumulative effect of those rational responses, made year after year by different institutions and funding bodies, is that the Aleutian Trench continues to receive very little direct scientific attention. There is a small irony here that is worth sitting with for a moment. The Aleutian region is not unknown to science. It is actually fairly well studied in certain respects. The atmospheric science community has been interested in the Aleutian Low for decades because of its role in large-scale climate patterns. The fisheries science community has worked extensively in the Bering Sea and the waters around the island chain because the region supports some of the most productive commercial fisheries in the world. Seismologists monitor the subduction zone continuously. There are research stations, weather stations, and monitoring networks distributed across the island chain. The Aleutian region is not scientifically ignored. It is just that the specific combination of deep-sea, biological and geological work that would illuminate the trench itself has not happened in any sustained way, and the operational reasons for that gap are as much about the surface of the ocean as about what lies beneath it. Deep-sea landers and ROVs are designed with a great deal of engineering care, but they are not designed to be deployed in conditions that no reasonable ship captain would operate in. The equipment assumes a certain baseline of surface stability, not because engineers failed to anticipate bad weather, but because there is a physical limit to what can be managed from a moving ship deck in heavy seas. A lander that weighs several hundred kilograms with its ballast weights and instrument packages attached, being lowered over the side of a ship on a winch in 2-metre swells is already a careful operation. In 6-metre swells, the same operation becomes genuinely dangerous, both for the equipment and for the people handling it. The sea does not make exceptions for scientific importance. Recovery is in some ways even more delicate than deployment. When a lander releases its ballast and ascends, it surfaces somewhere in the vicinity of the ship, and the crew must locate it visually or by radio beacon and retrieve it before weather or current carries it away. The lander floats at the surface, low in the water, and in rough conditions it can be very difficult to see. Recovery operations in heavy weather have resulted in lost equipment at other trench sites, and the Aleutian region's baseline conditions make that risk substantially higher than in calmer parts of the ocean. A lost lander in the Aleutian Trench, carrying months of biological samples from the Hadal zone, would be a significant scientific and financial loss, and the probability of that outcome is not negligible. None of this means that deep-sea work in the Aleutian region is impossible. It means it is difficult in ways that compound on each other, and that the combination of a narrow operational window, remote port infrastructure, long transits, rough surface conditions, and an actively seismic seafloor creates a set of challenges that no single one of which would be decisive, but that together make the Aleutian Trench a genuinely hard place to study. Scientists are not avoiding it because they are uninterested, or because there is nothing there worth finding. They are dealing with a location that demands more resources, more planning, more risk tolerance, and more logistical support than most comparable deep-sea targets, and that demand has not yet been met by the available combination of funding, institutional will, and practical opportunity. What makes this particularly interesting is that the operational difficulty sits entirely at the surface and in the upper water column. Once a lander is on the trench floor, it is in some sense insulated from the weather above. The Hadal zone at 7,600 metres is cold and dark and under enormous pressure, but it is not being tossed around by a storm. The storm is a problem for the ship and the crew and the deployment team. The trench floor itself is, in its own way, a stable environment, or at least a consistently extreme one. The difficulty is getting there and getting back. It is the interface between the ocean surface and the deep that presents the operational barrier, not the deep itself. Which is a strange thing to think about, that one of the main reasons we know so little about the bottom of the Aleutian Trench is because of what happens 7.5 kilometres above it. And yet, even if you could somehow solve the surface weather problem entirely, even if you had a ship that could hold perfect station in any conditions, and a crew that could deploy and recover equipment in any sea state, and a port with full research infrastructure just an hour's transit away, you would still be facing a set of challenges that have nothing to do with the weather or the logistics. Because the trench floor itself presents its own category of scientific difficulty, one that is quieter and slower moving than a storm, but in some ways just as obstructive. The bottom of the Aleutian Trench is not a clean, hard surface waiting to be sampled. It is something considerably more complicated than that, and understanding what the seafloor is actually made of down there and why it makes scientific work harder requires looking at a process that has been building up for millions of years. The word turbidite is not one that comes up often outside of geology, but it describes something that matters a great deal to anyone trying to understand what the floor of the Aleutian Trench actually looks like. A turbidite is, in simple terms, the deposit left behind by an underwater avalanche. When sediment accumulates on a steep slope, whether on the continental shelf or on the inner wall of a trench, it can reach a point where it is no longer stable. An earthquake, a small shift in pressure, sometimes just the gradual weight of more sediment piling on top, can trigger a turbidity current, a dense, fast-moving flow of sediment and water that rushes down the slope and spreads across the floor below. These flows can travel for hundreds of kilometres. They carry sand, silt, organic material, and whatever happens to be living in the sediment at the time. And when they finally slow and settle, they leave behind a distinct layer, graded from coarser material at the bottom to finer material at the top, that geologists can read like a page in a very long book. The Aleutian Trench has been accumulating these pages for millions of years, and the result is a sediment column of unusual thickness. In some parts of the trench, particularly along the sections closest to the Alaskan continental margin, sediment thickness has been estimated to exceed 3 kilometres. 3 kilometres of accumulated material, layer upon layer, each one representing some past disturbance, some past flow of material down from the shelf above. This is not typical for ocean trenches. Many deep trenches, particularly those far from continental margins, have relatively thin sediment layers. The Mariana Trench, for instance, has a comparatively modest sediment cover in its deepest sections, partly because it sits far from any large landmass, and therefore receives much less input from river systems and coastal erosion. The Aleutian Trench, by contrast, sits adjacent to one of the most geologically active and erosionally productive margins in the Northern Hemisphere. The Alaskan coastline contributes enormous quantities of sediment to the ocean, carried by rivers, moved by glaciers, and delivered to the shelf edge where it eventually, over time, finds its way into the trench. What this means in practical terms is that the floor of the Aleutian Trench is soft. Not soft in a comfortable way, but soft in the way that makes sampling genuinely difficult. When a lander touches down on a hard basalt surface, it lands cleanly. Its instruments have a stable platform, and any biological material on or near the seafloor is relatively accessible. When a lander touches down in deep, unconsolidated sediment, things get more complicated. The lander may sink partially into the substrate. Sediment can be disturbed by the impact and by the current created as the lander descends, potentially scattering the very organisms you're trying to observe or capture. Baited cameras, which are among the most common tools used in Hadal research, attract scavengers over a period of hours or days, but if the surrounding sediment is easily disturbed, even the slow movement of amphipods across the seafloor can create a kind of low-level turbidity that reduces image quality. The sediment is not just background. It is an active part of the environment, and in the Aleutian Trench, it is a very large and mobile part. The seismic connection makes this worse in a specific way. Because the trench sits directly above one of the most active subduction zones on Earth, turbidity currents here are not rare historical events. They are a recurring feature of the environment. Every significant earthquake along the Aleutian Arc has the potential to trigger new sediment flows down the trench walls. The 1946 earthquake, the 1957 event, the 1965 Rat Islands earthquake, each of these almost certainly disturbed the sediment column in the trench to some degree, rearranging material, burying older layers, and potentially displacing or destroying communities of organisms living at or near the seafloor. This is not speculation. Turbidite deposits triggered by large earthquakes have been documented in other subduction trenches, including the Japan Trench, where the 2011 Tohoku earthquake generated substantial sediment flows that were later studied by research vessels. The Aleutian Trench, with its longer history of major seismic events and its greater sediment supply, has almost certainly experienced similar dynamics repeatedly through its history. For scientists trying to understand what lives in the Hadal zone of the Aleutian Trench, this creates a problem that goes beyond the physical difficulty of sampling. The sediment environment itself shapes what organisms are present, how they live, and what they eat. Hadal fauna are not simply deep-sea fauna that happen to live at greater pressure. They are communities adapted to the specific conditions of trench floors, which include the particular chemistry, texture, and organic content of the local sediment. In trenches with thin, hard substrates, the biological community looks different from trenches with thick, soft, organic-rich sediment. The Aleutian Trench, with its heavy sediment input from the Alaskan margin, likely delivers substantial quantities of organic material to the Hadal zone, which could in principle support a relatively productive biological community. Organic material from land, from the continental shelf, from the productive surface waters of the Bering Sea and the North Pacific, all of it eventually sinks, and a significant fraction of it accumulates in the deepest part of the basin, which is the trench itself. But the same sediment that delivers this organic food source also buries things. Organisms living at or just below the sediment surface can be covered by turbidite flows. Slower moving in faunal communities, animals that live within the sediment rather than on its surface, may be periodically disrupted by sediment reworking. The chemical environment within the sediment changes with depth below the surface, with oxygen levels dropping and methane and sulfide concentrations potentially rising in the deeper layers. This creates a vertically stratified chemical world within the sediment column itself, separate from the vertical stratification of the water column above. Understanding what lives in this environment and how it functions requires not just sampling the surface of the trench floor, but sampling within the sediment, which demands a different kind of equipment and a much more precise deployment. There is also the question of what the sediment obscures. When you look at a photograph of the floor of the Aleutian Trench, you're looking at a relatively clear image of what is actually there. The substrate is visible, the organisms moving across it are visible, and the spatial relationships between different features of the environment are readable. In a trench with 3 kilometers of soft, easily disturbed sediment, the floor you photograph may not represent the full biological picture. Animals may be buried. Chemical gradients may be supporting microbial communities deep within the sediment that have no surface expression at all. The photograph shows you the top layer, but the top layer in the Aleutian Trench is just the most recent page of a very long and complicated document, and most of that document is invisible to any camera sitting on the surface of it. This is part of what makes the Aleutian Trench scientifically interesting in a way that is different from simply being deep. It is not just a deep hole. It is a deep hole that has been accumulating material from one of the most productive and geologically active margins in the world for tens of millions of years. The sediment record in the Aleutian Trench is, in a sense, a geological archive. Each layer records something about the conditions at the time it was deposited, the chemistry of the water, the organic material available, the seismic events that rearrange things, the biological communities that lived and died and were buried. Reading the archive would require coring equipment capable of penetrating deep into the sediment column, and doing that at Hadal depths, in an actively seismic environment, under the surface conditions of the Aleutian region, is a formidable undertaking. It has not been done in any comprehensive way. The contrast with the Mariana Trench is worth dwelling on for a moment, not to diminish the Mariana, which is genuinely extraordinary, but to illustrate how different these two environments are despite both being deep ocean trenches. The Mariana sits in a part of the Pacific that is geologically older and more stable, far from any major continental margin, in waters that are relatively calm at the surface. Its sediment layer is thin. Its walls are steep but not actively delivering avalanches of material on any regular basis. It is, in the context of Hadal trenches, a relatively clean and accessible scientific target. The Aleutian Trench is almost the opposite in every relevant respect. It is younger, more active, more sediment-rich, more physically dynamic, and surrounded by some of the worst surface weather on the planet. If the Mariana is a difficult place to study, the Aleutian is difficult in a different key entirely. And yet the sediment is not only an obstacle, it is also potentially one of the most scientifically valuable things about the trench. Sediment cores from other subduction zone trenches have yielded remarkable records of past earthquakes, past tsunamis, past changes in ocean chemistry and biological productivity. The sediment in the Aleutian Trench, if it could be properly sampled, might contain a detailed record of every major seismic event along the Aleutian Arc going back millions of years. It might contain chemical signatures of past changes in the North Pacific circulation, or biological markers that tell us something about how Hadal communities respond to periodic disturbance. The sediment is both the problem and the prize, which is a somewhat uncomfortable position for scientists to be in. There is a practical dimension to this that is easy to overlook. When researchers plan a deep-sea expedition, they are not just planning for the ideal case. They are planning for a range of possible outcomes, including equipment problems, weather delays, and sampling failures. In a trench with thick, soft sediment and active seismicity, the probability of a sampling failure, of a lander that sinks too deep into the substrate, or a core that collapses before it can be retrieved, or a baited camera that captures nothing because a small earthquake disturbed the sediment and dispersed the local fauna, is meaningfully higher than its more stable environment. Expedition planning involves risk assessment, and the Aleutian Trench scores poorly on several risk categories simultaneously. This does not make it impossible to study. It makes it a place where the expected return on a given investment of ship time and equipment is less predictable. And in a world where scientific funding is finite and competitive, unpredictability is its own kind of deterrent. What is perhaps most striking about the sediment situation is how little we actually know about its biological consequences. we can reason about what thick, earthquake-disturbed sediment probably means for Hadal communities based on what we know from other environments. But the Aleutian Hadal zone has not been sampled in enough detail to tell us whether those predictions are correct. It is possible that the regular sediment disturbance is selected for a particularly resilient community of organisms, adapted to periodic burial and chemical disruption in ways that make them unlike Hadal fauna anywhere else. It is possible that the organic richness of the sediment supports biomass densities that would surprise researchers accustomed to the more oligotrophic conditions of other trenches. It is possible that the sediment chemistry, with its methane and sulfide gradients, supports microbial communities that are doing something chemically unusual. All of these are genuine scientific possibilities, not speculation dressed up as fact, but real open questions that the available data cannot answer. The fragments of biological data that do exist from the Aleutian Hadal zone come mostly from expeditions that took place decades ago, before modern sampling technology existed, and they suggest that life is present at depth, but they do not give us the resolution needed to understand how that life is organised or what is driving it. What the sediment represents in the end is a layer of complexity that sits between the scientific questions and any straightforward answer to them. It is not just deep and dark down there. It is deep, dark, and buried under millions of years of accumulated material, all of it moving, all of it chemically active, all of it shaped by a geological process that has not stopped and shows no sign of stopping. Getting past that layer, literally and figuratively, is one of the central challenges of studying this particular trench, and it is a challenge that compounds every other difficulty already stacked against it. Which brings us to the question of what we actually know about what lives there, because despite everything, there is some biological data. It is old, it is incomplete, and it raises more questions than it answers, but it exists, and it tells us something important about what the Aleutian Hadal zone is and is not. The biological record from the Aleutian Hadal zone is, to put it plainly, thin. Not non-existent, but thin in the way that a single photograph of a city tells you the city exists without telling you much about how it actually works. What we have comes largely from a period of ocean exploration that feels almost impossibly distant from the present, not just in time, but in methodology and ambition. During the 1950s and 1960s, Soviet research vessels conducted a series of deep-sea trawling expeditions across the North Pacific, including passes over the Aleutian Trench. These were ambitious programs, part of a broader Soviet effort to document the deep ocean during the same era that produced some of the earliest biological data from the Kuril-Kamchatka Trench and other Pacific Hadal zones. The ships were not equipped with anything resembling modern deep-sea technology. There were no remotely operated vehicles, no high-definition cameras, no real-time telemetry from the seafloor. What they had were trawl nets, long cables, and a great deal of patience. The trawls brought things up, that much is certain. From Hadal depths in the Aleutian Trench, Soviet researchers recovered specimens of amphipods, which are small crustaceans that look something like a shrimp that has been gently compressed from the sides. They also recovered polychaete worms, which are segmented marine worms that come in an almost bewildering variety of forms and are found in virtually every marine environment, from tidal pools to the deepest ocean floors. Holothurians were present as well, the sea cucumbers, soft-bodied animals that move slowly across the sediment, consuming organic material, and are, in a quiet way, ecologically important in deep-sea environments. And there were bivalves, relatives of the clams and mussels found in shallower waters, present even at those extreme depths in forms adapted to the cold, high-pressure conditions of the Hadal zone. The presence of these animals was not, in itself, surprising to the researchers who found them. By the mid-20th century, it was already understood that the deep ocean was not biologically empty, despite what earlier generations of scientists had assumed. What the Soviet trawl data contributed was a confirmation that the Aleutian Hadal zone followed a broadly similar pattern to other trenches, supporting a community of organisms capable of surviving at depths where pressure, cold, and darkness would seem to make life difficult. But the data was coarse. Trawl nets are not precise instruments. They collect whatever they happen to sweep through, and they do it in a way that damages many specimens and provides no information about where exactly in the water column or on the seafloor a given animal was living. You know something was there. You do not know what it was doing, how many of them there were, or what the environment around them looked like. Among the organisms recovered, the amphipods are worth pausing on for a moment, because they have turned out to be one of the most scientifically interesting groups in the Hadal world. Specifically, amphipods of the genus Hirondelia have been found in the deepest zones of the Aleutian Trench, as they have in many other Hadal environments. Hirondelia are scavengers, extraordinarily well adapted to the extreme conditions of Hadal depths. They have been found in virtually every trench that has been sampled adequately, from the Mariana to the Kermadec to the Puerto Rico Trench in the Atlantic. They aggregate rapidly around food falls, which are the carcasses of fish, whales or other animals that sink from the surface and represent a concentrated burst of nutrition in an otherwise food-limited environment. A single whale fall in a Hadal trench can attract thousands of amphipods within hours, which is a remarkable thing to consider given the apparent emptiness of the surrounding environment. What makes the Hirondelia records from the Aleutian Trench both interesting and frustrating is that they confirm the presence of a biologically active Hadal community while telling us almost nothing about its character. Hadal amphipod populations vary considerably between trenches in terms of density, body size, species composition, and behaviour. Some of this variation appears to be related to the organic input from the surface, which determines how much food is available. Some of it may be related to sediment conditions, water chemistry, or the physical structure of the trench. The Aleutian Trench, with its high sediment input from the Alaskan continental margin, and its proximity to one of the most biologically productive stretches of the North Pacific, might be expected to support relatively dense amphipod populations. The surface waters of the North Pacific subarctic region are enormously productive, with seasonal blooms of phytoplankton that send pulses of organic material sinking toward the seafloor. Some fraction of that material eventually reaches Hadal depths, and in a trench position directly beneath that productive zone, the organic input to the Hadal community could be substantial. But whether it actually is, and what effect that has on the biological community living at the bottom of the Aleutian Trench, is something the Soviet-era trawl data cannot tell us. There is also the question of what has changed since those expeditions were conducted. 60 or 70 years is not a long time in geological terms, but it is a meaningful period in terms of ocean conditions. The North Pacific has warmed, circulation patterns have shifted, the productivity of the subarctic gyre has changed in ways that are still being studied. If the biological community at the bottom of the Aleutian Trench is sensitive to changes in organic input from the surface, and there is good reason to think Hadal communities are at least somewhat responsive to such changes, then the data collected in the 1950s and 1960s may not accurately reflect what is there today. This is not a purely theoretical concern. In other deep-sea environments, researchers have documented changes in community composition and biomass over decadal timescales, linked to changes in surface productivity. Without a modern baseline from the Aleutian Hadal zone, we have no way of knowing whether the community has changed, and if so, how. The absence of modern, high-resolution biological data from the Aleutian Hadal zone is, when you think about it, a fairly striking gap. Not in the sense that it represents a failure of science, but in the sense that it illustrates how unevenly the deep ocean has been explored. As of the early 2020s, there is no publicly available ROV footage from the Hadal zone of the Aleutian Trench. No video of the sea floor at those depths, no high-definition images of the organisms living there, no real-time observations of how animals behave in that environment. For comparison, the Mariana Trench has been visited by remotely operated vehicles multiple times, and the footage from those dives has produced genuinely remarkable observations, including new species, unexpected behaviours, and detailed images of the physical environment. The Kermadec Trench has been visited by modern lander systems. The Tonga Trench has been explored as part of the Five Deeps expedition. The Aleutian Trench, which is longer than any of these and sits in a geologically extraordinary location, has not received that kind of attention. Part of what makes this gap feel significant is that the biology of Hadal trenches has turned out to be far more interesting and varied than many researchers expected. Each trench that has been studied in detail has yielded surprises, organisms or behaviours or ecological relationships that were not predicted from what was known before the dive. The Japan Trench produced observations of snail fish, members of the family Lipiridae, living at depths that push the theoretical limits of what vertebrates can survive, given the effects of pressure on certain biological molecules. The Mariana Trench revealed a complex community of microorganisms in the sediment that were metabolically active in ways that were not anticipated. The Kermadec Trench showed amphipod populations with contamination levels that surprised and disturbed researchers. Each of these discoveries came only because someone actually went there with modern equipment and looked. The Aleutian Trench has not had its equivalent moment, and so its surprises, whatever they are, remain unobserved. There is something a little strange about sitting with that fact. The trench has been known as a geographical feature for well over a century. Its general location and dimensions have been understood for decades. The Soviet expeditions confirmed that life exists in its Hadal zone, and yet the specific character of that life, the species present, their densities, their behaviours, their ecological relationships, the physical environment they inhabit at the level of detail that modern instruments can provide, all of that remains essentially unknown. It is not hidden by any particular mystery. There is no great scientific controversy about whether the Aleutian Hadal zone is worth studying. It is simply a place that the combination of logistical difficulty, funding constraints, and scientific prioritization has consistently passed over in favour of more accessible targets. The fragments of data that do exist suggest a community that is biologically real and probably ecologically complex. Amphipods, polychaetes, holothurians, bivalves. These are not organisms that exist in isolation. They are part of food webs, part of nutrient cycling processes, part of a broader ecological system that connects the Hadal floor to the water column above it, and through that to the surface ocean and ultimately to the atmosphere. Understanding how that system works in the Aleutian Trench specifically would contribute to a broader understanding of how Hadal ecosystems function across different geological and oceanographic contexts. The Aleutian Trench is not just another deep hole. It is a deep hole in a specific place, shaped by specific forces, receiving specific inputs from a specific surface environment, and the biology at its bottom is almost certainly shaped by all of those specifics in ways that would be scientifically meaningful to document. What the Soviet-era data cannot tell us is perhaps best summarized by what it cannot even ask. Modern Hadal biology is interested in questions that were not part of the scientific vocabulary in the 1950s. Questions about microbial diversity and function, about the role of viruses in deep-sea ecosystems, about the genetic adaptations that allow organisms to function under extreme pressure, about the chemical communication between organisms in food-limited environments, about the relationship between sediment chemistry and community composition. None of these questions can be addressed with TrawlNet data from 60 years ago. They require modern molecular tools, modern imaging systems, modern in-situ sensors, and direct access to the environment. Getting that access to the Aleutian Hadal zone is not impossible, but it has not happened yet, and the biological record from this trench remains frozen, in a sense, at the level of knowledge available to researchers working with the technology of the early Cold War period. It is worth noting that the very incompleteness of this record has a certain scientific value in itself. The gaps tell us something about how exploration has been prioritized, about which environments have been considered accessible or interesting or fundable, and which have been quietly set aside. The Aleutian Trench is not the only understudied Hadal zone, but it may be one of the most striking examples of a place that is simultaneously important, scientifically interesting, and persistently overlooked. The biological data we have is old enough that it raises as many questions as it answers, and modern enough in its implications that those questions feel genuinely urgent rather than merely academic. What the organisms recovered from the Aleutian Hadal zone are doing down there, how they are adapted to the specific conditions of that environment, whether the community is unusual in ways that would only become apparent with modern observation, all of this remains open, and the openness is not comfortable in the way that some scientific mysteries are comfortable. It is more like the feeling of knowing that a room in a building you care about has not been entered in decades, and not being entirely sure what you would find if you finally opened the door. Not dangerous exactly, not threatening, just genuinely unknown in a way that feels like it should not still be the case in the 21st century. The biological picture, such as it is, points toward a community that is present, that is probably more complex than the available data can show, and that is shaped by geological and oceanographic forces that make it potentially unlike Hadal communities anywhere else in the Pacific. Whether that potential is realized, whether the Aleutian Hadal zone turns out to be biologically extraordinary, or broadly similar to other trenches, is a question that cannot be answered from what we currently have. It requires modern equipment, modern methods, and a research expedition willing to contend with everything the Aleutian region throws at the people and machines trying to work there. And that brings us directly to the engineering dimension of the problem, because the biological questions are only part of the challenge. Getting modern instruments to the bottom of the Aleutian Trench is not simply a matter of deciding to go. The depth itself, 7,679 metres at the deepest point, creates engineering demands that are far more severe than most people realise, and the consequences of getting those demands wrong have, in at least one well-documented case, been catastrophic. 7,679 metres. It is worth sitting with that number for a moment before moving on, because it is easy to hear a depth figure and let it pass through without really registering what it means in physical terms. 7,679 metres is not simply a long way down. It is a distance that transforms the ocean from an environment that is merely hostile into one that operates according to physical rules that have almost no analogy in everyday human experience. The pressure at that depth, roughly 770 atmospheres, or somewhere around 11,300 pounds per square inch, is not a force that scales comfortably with intuition. It is the equivalent of stacking approximately 55 fully loaded Boeing 747 aircraft on a surface the size of your hand. That comparison sounds dramatic, but it is actually just the arithmetic. What that pressure does to materials is the real engineering story. Water, somewhat counterintuitively, is nearly incompressible, so the ocean itself does not collapse inward at Hadal depths. But almost everything humans build does compress, flex, deform, or fail in ways that are difficult to predict and very difficult to test without actually going to those depths. Camera housings made from aluminum or titanium must be machined to tolerances that account for the precise degree of compression the material will undergo at 770 atmospheres. A housing that is perfectly sealed at the surface may develop microscopic pathways for water intrusion once the metal has been compressed by the pressure column above it. Glass viewports, which are used for optical systems on deep-sea vehicles, are actually stronger under compression than metal in many configurations, which is why borosilicate glass spheres became a preferred housing material for deep-rated instruments. But glass also has failure modes that are sudden and total. A flaw in the glass, a small inclusion or surface scratch, can propagate under pressure in milliseconds, and when a glass sphere at Hadal depth fails, it does not leak. It implodes. Battery systems present a different category of problem. Most lithium-ion batteries used in underwater vehicles are pressure-tolerant to a point, but the chemistry of the cells is affected by both pressure and temperature, and the Aleutian Hadal zone is cold, somewhere around 1 to 2 degrees Celsius at those depths. Cold reduces battery capacity, sometimes significantly, which shortens the operational window of a vehicle that may need many hours to descend, work, and ascend. Some deep-rated systems use oil-compensated battery housings, where the interior pressure is equalized with the exterior by filling the housing with a non-conductive oil that compresses slightly as depth increases. This works, but it adds complexity, weight, and maintenance requirements that compound the logistical challenges of operating in a remote location. Thrusters are another point of vulnerability. The motors that drive ROV thrusters must be sealed against water intrusion, while still allowing the motor shaft to rotate freely. At shallow depths, this is a solved engineering problem. At Hadal depths, the pressure differential across the seal is so extreme that conventional shaft seals fail, and the solutions involve either pressure-compensated motor housings or magnetically coupled drives that eliminate the shaft penetration entirely. Both approaches work, but both add cost and complexity, and both have failure modes that become more likely with increasing depth. Sample containers are a problem that often gets overlooked in popular accounts of deep-sea exploration, but they are genuinely important for scientific work. If you recover a biological sample from 7,679 meters and bring it to the surface, the pressure drops from 770 atmospheres to 1 atmosphere over the course of the ascent. Organisms that were living under extreme pressure are dead long before they reach the surface, and their tissues, cell membranes, and biochemistry have been altered by the decompression. This is not unique to the Aleutian Trench. It is a universal problem in Hadal biology, but it means that understanding the physiology and biochemistry of Hadal organisms requires either specialized pressure-retaining samplers that maintain depth pressure throughout the recovery process, or molecular techniques applied to recover tissue that can infer in situ conditions from preserved samples. Pressure-retaining samplers exist, but they are expensive, mechanically complex, and not standard equipment on most research vessels. The depth of the Aleutian Trench's deepest point, 7,679 meters, sits in a range that is particularly awkward from an engineering and logistics standpoint. The majority of research-grade remotely operated vehicles and autonomous landers currently in operation are rated to 6,000 meters. That depth rating covers the vast majority of the ocean floor. Roughly 98% of the seafloor lies shallower than 6,000 meters, which means a 6,000 meter rated vehicle is genuinely useful for most oceanographic research. But the Hadal zone, by definition, begins at 6,000 meters, and the Aleutian Trench's deepest sections are nearly 1,700 meters below that threshold. That gap is not trivial. It represents an additional 170 atmospheres of pressure, and engineering systems to handle that additional load requires essentially rebuilding the vehicle from a pressure-tolerant standpoint. You cannot simply take a 6,000 meter rated ROV and reinforce it to reach 7,679 meters. The pressure housing geometries, the seal designs, the glass ratings, the cable specifications, all of these have to be redesigned from the ground up for the higher pressure class. Full ocean depth vehicles, those rated to 11,000 meters to cover even the deepest point in the Mariana Trench, exist, but they are rare and expensive. The WHOI hybrid remotely operated vehicle Nereus was one of the most capable full-depth vehicles ever built, able to operate either as a tethered ROV or as an autonomous vehicle, and it successfully reached the bottom of the Challenger Deep in 2009. It was a genuinely remarkable piece of engineering. In May 2014, Nereus was operating in the Kermadec Trench at a depth of approximately 9,990 meters when it was lost. The vehicle stopped communicating, debris was recovered at the surface, and the most likely explanation, based on the nature of the debris, was an implosion caused by pressure failure of one of its glass housings. The loss of Nereus was significant not just because it was a costly vehicle, somewhere in the range of $8 million to build, but because it demonstrated in a very direct and irreversible way that full ocean depth engineering is not a solved problem. The pressure at those depths is not forgiving of design margins that are too thin, and even carefully engineered systems can fail in ways that are catastrophic and unrecoverable. The loss of Nereus had a measurable effect on institutional caution around full-depth vehicle operations. It did not stop deep-sea exploration, but it reinforced the understanding that vehicles operating at Hadal depths are operating at the edge of what current engineering can reliably achieve, and that the consequences of getting it wrong are total. You do not recover a vehicle from 10,000 meters after an implosion. You recover debris. This awareness is part of the background context for any discussion of why sending equipment to the bottom of the Aleutian Trench is not simply a matter of scheduling a cruise and deploying a lander. The DSV limiting factor, built by Triton submarines and used during the 5 Deeps expedition between 2018 and 2019, is currently one of the few operational full ocean depth vehicles in existence. It is a crewed submersible, which adds another dimension of engineering complexity, since human life support systems must also function at full ocean depth. The limiting factor successfully reached the bottom of all 5 of the world's ocean basins, including the Challenger Deep, and it has continued to be used for scientific expeditions since the 5 Deeps project concluded. It represents the current state of the art in terms of what can actually reach the deepest parts of the ocean. But access to the limiting factor is not straightforward. It is operated by a private entity, Inkfish, and deploying it requires the support vessel DSSV pressure drop, logistical coordination, and funding arrangements that are not trivial to assemble. It is not equipment that a research team can simply request through a standard ship time application process. The cost dimension of full depth rated equipment is worth dwelling on for a moment, because it shapes the entire landscape of Hadal research in ways that are easy to underestimate. A standard oceanographic research cruise to a remote location like the Aleutian region might cost anywhere from $20,000 to $50,000 per day when you factor in ship time, fuel, crew, and equipment operations. A full-depth rated lander system, the kind that can actually reach 7,679 meters and return data and samples, cost hundreds of thousands of dollars to build and maintain. A full-depth ROV or submersible is in the tens of millions of dollars range, and all of this equipment must be transported to and operated from a ship that is itself in one of the stormiest patches of ocean on the planet. The financial arithmetic of a serious Aleutian Hadal expedition is daunting, even before you account for the probability that weather will cut the operational window short, or that equipment problems will reduce the number of deployments achievable in a given cruise. There's also the question of what happens if something goes wrong at depth. In calm, well-studied trench environments with good logistical support, a vehicle loss is a serious setback, but a manageable one. In the Aleutian region, where the weather can deteriorate rapidly and the nearest significant port infrastructure is Dutch Harbour, a vehicle loss combined with a weather event could turn a difficult situation into a genuinely dangerous one for the ship and crew. Risk assessments for scientific expeditions are real documents that real institutions take seriously, and the Aleutian region scores poorly on several of the variables that go into those assessments. It is also worth noting that the 7,679 metre depth of the Aleutian Trench is not uniformly distributed along the trench's length. The trench is over 3,400 kilometres long, and much of it is shallower than the deepest point near Atu Island. The deepest sections are also the most remote, the farthest from any port, the most exposed to weather coming off the North Pacific, and the least likely to be reachable within a narrow weather window. So even if a research team has the equipment and funding to attempt a deployment, the specific geography of the deepest zone creates additional logistical complications that do not apply to a trench like the Mariana, which is both accessible from Guam and situated in a part of the Pacific that, while not calm, is considerably less hostile than the Aleutian region in winter. None of this means that reaching the Aleutian Hadal zone is impossible. It clearly is not. The engineering exists, even if it is expensive and rare. The depth, while challenging, is within the range of what full ocean depth vehicles can handle. But the combination of factors, the pressure requirements, the equipment costs, the weather exposure, the remoteness, the institutional memory of vehicle losses at Hadal depths, all of these converge to make the Aleutian Trench a particularly difficult target compared to other Hadal zones that have received more attention. And when funding agencies and research institutions are making decisions about where to direct limited resources, a difficult target with high costs and high risk of operational problems tends to lose out to targets that offer a better return on the investment of time and money. The engineering story of the Aleutian Trench is, in a sense, the story of a place that sits just beyond the comfortable reach of most available tools and just outside the logistical comfort zone of most research programs. The 7,679-metre depth is deep enough to require full depth-rated equipment, but not so dramatically deep that it attracts the kind of record-chasing interest that drove expeditions to the Challenger Deep. It is remote enough to be genuinely difficult to reach, but not so remote that it has acquired the romantic appeal of truly extreme destinations. It occupies an awkward middle ground where the difficulty is real, but the drama is not obvious, and in a world where scientific resources are finite and expedition planning is competitive, awkward middle grounds tend to wait. What the engineering constraints mean in practice is that the biological questions raised by the Soviet-era data, the questions about what is actually living in the Aleutian Hadal zone and how those organisms are adapted to their specific environment, cannot be answered with the equipment that most research institutions have readily available. Answering them requires either access to full depth-rated systems or the development of new approaches, like autonomous landers designed specifically for the depth and environmental conditions of the Aleutian Trench, that might reduce cost and risk while still delivering useful data. And that brings the conversation naturally to another dimension of the problem, one that is less about engineering and more about how scientific priorities are set and how funding flows towards some questions and away from others, even when the scientific case for attention is genuinely strong. The story of how scientific funding actually works in practice is one that rarely gets told in the same breath as stories about deep-sea exploration, but it shapes almost everything about which places get studied and which ones wait. It is worth spending some time with it, because when you look at the Aleutian Trench's history of neglect, the funding picture is at least as explanatory as the engineering picture, and in some ways more so. The Hades program, which stands for Hadal Ecosystem Studies, was funded by the National Science Foundation beginning around 2012 and represents one of the most significant coordinated efforts to study Hadal environments that has ever been mounted in the United States. It was a serious, well-resourced program with real scientific ambition, and the researchers involved produced genuinely important work on the biology, chemistry, and ecology of the deepest ocean zones. The program ran for several years and generated a body of literature that substantially advanced the field of Hadal science. If you have read anything about amphipods at extreme depths, or about microbial communities in Hadal sediments, or about the food web dynamics that sustain life in trenches, there is a reasonable chance that work was connected to Hades in some way. But the trenches that Hades focused on were the Mariana, the Kermadec, and the Tonga, not the Aleutian. The reasons for that choice are not hard to understand once you look at them. The Mariana Trench had decades of prior research to build on, going back at least to the Challenger Deep soundings of 1875 and the Trieste dive of 1960. It had existing data sets, existing logistical frameworks, and a kind of scientific infrastructure that made new expeditions easier to plan and justify. The Kermadec Trench, northeast of New Zealand, is accessible from Auckland and Tonga, sits in relatively manageable Pacific waters, and had been studied enough to provide a useful scientific baseline. The Tonga Trench, similarly, offered accessibility and prior data. These were not arbitrary choices. They were the choices that made logistical and scientific sense, given the resources available and the state of the field at the time. The Aleutian Trench, by contrast, had almost none of that infrastructure. The biological data from Soviet-era expeditions was fragmentary and difficult to build on directly, partly because the methods used in the 1950s and 1960s were different enough from modern approaches that direct comparison is complicated, and partly because that data was not always fully integrated into the English language scientific literature in ways that made it easily accessible to American researchers writing NSF proposals. The logistical challenges were real and well understood, and there was no existing community of researchers who had built careers around the Aleutian Hadal zone in the way that careers had been built around the Mariana or the Kermadec. When a funding program is deciding where to direct resources, the presence or absence of an established research community matters enormously, because that community is what produces the proposals, the preliminary data, and the scientific arguments that make a funding case compelling. This is the self-reinforcing nature of scientific attention, and it operates in deep-sea research just as it does in every other scientific field. A trench that has been studied attracts researchers who study it further, who produce publications, who generate preliminary data, who write successful proposals, who get ship time, who produce more publications. A trench that has not been studied lacks all of those things, which makes it harder to write a compelling proposal, which means it is less likely to receive funding, which means it continues to lack the data and the research community that would make it easier to fund in the future. The Aleutian Trench is caught in this loop, and it has been caught in it for a long time. It is not that program officers at the National Science Foundation looked at the Aleutian Trench and decided it was unimportant. That is almost certainly not what happened. It is more that the combination of logistical difficulty, limited prior data, and the absence of an established research community meant that the Aleutian Trench simply did not generate the kind of competitive proposals that other trenches did. And in a system where funding is allocated based on the strength of proposals, a place that is hard to write a strong proposal about tends to lose out to places that are easier to write about, even when the scientific questions it raises are genuinely interesting. There's also a subtler dynamic at work, which has to do with how scientific fields define their frontiers. In the early 2010s, when Hades was being designed, the Challenger Deep was still the defining target of Hadal ambition. It was the deepest point, the most extreme environment, the place that carried the most symbolic weight. Funding a program centered on the Mariana Trench meant funding work at the absolute frontier of the field, which is a compelling narrative both scientifically and in terms of public engagement. The Aleutian Trench, at 7,679 metres, is genuinely deep, genuinely Hadal, and genuinely understudied, but it does not carry the same symbolic charge. It is not the deepest. It is not the most extreme. It is, in the language of competitive grant writing, a harder sell, even if the scientific case for studying it is solid. There is something a little frustrating about this if you think about it too long. The Aleutian Trench is one of the longest trenches on Earth, one of the most seismically active, one of the most poorly understood biologically, and one of the most logistically challenging to access. Those are all good reasons to study it, but in a funding environment where proposals compete against each other, and where the strength of a proposal depends partly on prior data and established research communities, good reasons are not always sufficient. You also need the infrastructure of prior attention, and the Aleutian Trench has very little of that. It is worth noting that geological and seismic studies of the Aleutian subduction zone have received consistent funding over the decades, because the earthquake and tsunami hazard is real, and the public safety implications are obvious. The Alaska Earthquake Center, the National Tsunami Warning Center, and various university research groups have produced substantial work on the seismicity of the Aleutian Arc, the structure of the subduction zone, and the potential for future large earthquakes. But this work is focused on the subduction system as a whole, not specifically on the Hadal zone of the trench. It is concerned with fault geometry, slip rates, and tsunami generation mechanisms, not with what lives at the bottom of the trench or what the sediment chemistry looks like at 7,000 metres. The seismic research community and the Hadal ecology research community are largely separate, and the Aleutian Trench falls through the gap between them. It is studied by seismologists for reasons that have nothing to do with its biology. and it is not studied by biologists partly because the seismologists have not generated the kind of biological baseline data that biologists would need to build on. The gap between these two communities is actually one of the more interesting structural features of Aleutian Trench science, if you can call it that. There is a reasonable argument that a place where active subduction is occurring, where the seafloor is geologically dynamic, where sediment is being displaced by earthquakes, and where fluid expulsion from the subducting plate may be creating unusual chemical environments, is exactly the kind of place where biology and geology need to be studied together. The biological communities in such an environment are not independent of the geological processes. They are shaped by them, dependent on them, and potentially recording them in ways that purely geological studies would miss. But integrated, cross-disciplinary expeditions to remote, logistically difficult environments require a level of coordination and funding that is genuinely hard to assemble, and the Aleutian Trench has not yet been the subject of that kind of coordinated effort. Some of the most productive deep-sea research programs in recent years have been those that managed to combine biological, chemical, and geological objectives within a single expedition, because that combination makes the scientific case stronger and the funding more defensible. The Hades program did some of this. The 5 Deeps expedition, which was privately funded and ran from 2018 to 2019, did this in a different way, using the DSV limiting factor to reach the deepest point in each of the world's 5 oceans and collecting biological and geological samples along the way. That expedition included a dive in the Malloy Deep in the Arctic and a dive in the Challenger Deep in the Pacific, but it did not include a dive in the Aleutian Trench. The deepest point of the Aleutian Trench near Attu Island was not one of the 5 ocean deepest points that the expedition was organised around, so it fell outside the scope of the mission. This is another version of the same pattern. The Aleutian Trench is deep enough to matter, but not quite deep enough to be the target of record-setting expeditions. It is remote enough to be difficult, but not remote enough to be romantically extreme. It is scientifically interesting, but the case for it has not been made loudly enough or consistently enough to compete successfully for the limited resources that Hadal research attracts. It is, in a sense, a victim of its own middling position in the hierarchy of deep-sea superlatives. What would it actually take to change this? That is a question worth asking, because it is not purely rhetorical. The scientific case for a serious Aleutian Hadal expedition is real. The biological questions left open by the Soviet-era data are real. The relevance to earthquake and tsunami science is real. The possibility of chemosynthetic communities associated with subduction zone fluid expulsion is real. The potential for the trench to hold a chemical record of North Pacific pollution is real. Any one of these would be a legitimate scientific justification for an expedition. Together, they make a compelling argument. The practical requirements would include access to a full ocean depth rated vehicle, which means either the DSV limiting factor or a future equivalent, since most research ROVs and landers top out at 6,000 metres, and the deepest Aleutian zone is nearly 1,700 metres below that threshold. It would require a ship capable of operating in North Pacific conditions, which is not an exotic requirement but does narrow the field of suitable vessels. It would require a weather window, which in the Aleutian region means planning carefully around seasonal conditions and accepting that the window may be shorter than desired. And it would require funding, which means either a successful NSF proposal, a partnership with a private expedition organisation like Inkay Fish, or some combination of the two. None of these requirements are impossible to meet. They are demanding, but not prohibitively so. The 5 Deeps expedition demonstrated that privately funded full ocean depth exploration is achievable in the modern era. The Schmidt Ocean Institute has shown that well-resourced non-governmental organisations can mount serious scientific expeditions to remote locations. The technology exists. The scientific questions exist. What has not yet come together is the specific combination of institutional will, logistical planning, and financial commitment that would make an Aleutian Hadal expedition happen. There is a certain irony in the fact that the very characteristics that make the Aleutian Trench scientifically interesting, its geological dynamism, its sediment complexity, its remote and storm-battered location, are also the characteristics that make it hard to fund and hard to reach. The trench is difficult to study precisely because it is the kind of place that rewards careful study. That is not a paradox that resolves itself easily, and the history of deep-sea research suggests that places like this tend to wait until either the technology becomes cheap enough or the scientific urgency becomes obvious enough to overcome the inertia. For now, the funding picture for the Aleutian Hadal Zone looks much as it has for the past several decades. Geological and seismic work continues, focused on the subduction system rather than the trench floor specifically. Biological work remains essentially absent at Hadal depths. The Soviet-era specimen collections sit in archives, representing the most detailed biological picture we have of a place that is 7,679 meters deep and thousands of kilometers long, and the scientific community, aware of the trench's existence and generally aware of its interest, continues to direct its limited resources toward targets that are easier to reach and easier to justify in competitive funding environments. What makes this worth thinking about carefully is not that anyone is making a bad decision. The researchers who study the Mariana or the Kermadec are doing important work. The program officers who fund accessible, well-justified projects are doing their jobs responsibly. The institutions that weigh risk and cost carefully before committing to remote, technically demanding expeditions are being appropriately cautious. The system is not broken. It is just producing a particular outcome, which is that the Aleutian Trench remains, in the language of Hadal science, essentially uncharacterized at its deepest levels. And underneath all of that, in the cold and dark below 6,000 meters, the trench continues to exist in a state of geological activity and biological occupation that we can only partially infer from old data and indirect evidence. Whatever is living down there, whatever chemistry is occurring in the sediment, whatever fluid pathways are moving through the subducting plate and emerging at the trench floor, all of it continues without any particular regard for the funding cycles and logistical challenges that keep it unobserved. That is perhaps the most striking thing about the Aleutian Hadal Zone. It does not need our attention to be interesting. It is interesting whether we look at it or not. The question is simply whether we will ever look closely enough to find out what is actually there. And that question leads naturally into another dimension of the trench's story, one that has to do not with money or engineering, but with what the geology of the trench floor itself might be hiding. So let's talk about what the geology of the trench floor might actually be hiding, because this is where the story takes a turn that most people do not expect when they first start thinking about deep ocean trenches. When most people picture the bottom of a trench, they imagine something cold and still, a flat, featureless expanse of sediment under enormous pressure, dark and quiet, biologically sparse. And in some trenches that picture is roughly accurate. But subduction zones are not passive environments. They are places where one tectonic plate is being forced beneath another, and that process is not clean or dry. It involves water. A lot of water, locked into the minerals of the subducting plate, squeezed out under pressure and pushed upward through the overlying sediment and rock. What comes up through those pathways is not just water. It is chemically altered fluid, carrying methane, hydrogen sulfide and other compounds that, at the surface, would simply be toxic. But at the seafloor, under the right conditions, they become the foundation of something remarkable. The phenomenon is called a cold seep, and it is worth explaining carefully because it is one of the more genuinely surprising things that deep-sea science has uncovered in the last few decades. Cold seeps are places where hydrocarbon-rich fluid, primarily methane, seeps up through the sea floor along fault lines or through permeable sediment. The word cold here is used to distinguish them from hydrothermal vents, which are associated with volcanic heat. Cold seeps occur at ambient deep water temperatures, which in the Hadal zone means just a few degrees above freezing. They are not dramatic in the visual sense. There is no superheated plume, no glowing mineral chimney. They're quieter than that. But around them, communities of organisms have evolved to make a living from the chemistry, rather than from sunlight or the rain of organic material from the surface. The key is chemosynthesis. At a cold seep, bacteria and archaea oxidize the methane and hydrogen sulfide coming up from below, producing energy in the process. These microorganisms form the base of a food web that supports tube worms, clams, mussels, shrimp, crabs, and a range of other organisms, all living in an environment where photosynthesis has never played any role whatsoever. The communities around cold seeps can be remarkably dense and diverse compared to the surrounding seafloor, which tends to be relatively sparse at Hadal depths. They're essentially oases, chemically powered islands of life in an otherwise food-limited environment. Cold seeps have been documented along subduction zones around the Pacific Rim for several decades now. The Cascadia margin, off the coast of Oregon and Washington, has been studied extensively since the 1980s, and the cold seep communities there are among the best characterized in the world. Tube worms of the genus Lamellibrachia have been found living at Cascadia seeps, and some of these organisms are estimated to be over 200 years old, growing extraordinarily slowly in the cold, methane-rich sediment. The Aleutian Trench, which is also a subduction zone environment, has documented cold seep communities at various depths, including some observations in the Hadal zone itself following the 2011 Tohoku earthquake, which appears to have altered fluid pathways along the trench floor and may have stimulated seep activity in certain areas. The Hikurangi margin off New Zealand, another subduction zone, has been the site of active cold seep research for years, with ROV surveys documenting methane bubble plumes, carbonate crusts, and chemosynthetic communities at multiple depth ranges. The Aleutian subduction zone, which is the same category of geological environment as all of these, shows geochemical indicators that are consistent with fluid expulsion. Studies of the sediment and water chemistry associated with the Aleutian margin have found elevated methane concentrations in some areas, along with other geochemical signatures that suggest active fluid movement through the subducting plate and overlying sediment. This is not a wild speculation. It follows directly from what we know about how subduction zones behave, and the Aleutian system is one of the most active subduction zones on Earth, which means the fluid processes associated with it are likely to be correspondingly active. The problem is that almost none of this has been directly observed at Hadal depths in the Aleutian Trench. There have been some studies of seep-related activity on the shallower portions of the Aleutian margin, in water depths reachable by conventional ROVs and research submersibles. But the deepest parts of the trench, the Hadal zone below 6,000 metres, have not been surveyed for cold seep activity in any systematic way. No ROV has descended into the Aleutian Hadal zone and looked for the characteristic features of a cold seep environment. The carbonate crusts that form when methane reacts with seawater, the bacterial mats that colonize seep-active sediment, the clusters of chemosymbiotic bivalves that are often the most visible sign of seep activity on the seafloor. This means that when scientists try to assess the biological character of the deepest Aleutian Trench, they are working with a significant blind spot. The Soviet-era trawl samples recovered amphipods and polychaetes and holothurians, organisms adapted to the cold, high-pressure Hadal environment and dependent largely on organic material sinking from above. These are the organisms you would expect to find in a standard Hadal setting. But if there are cold seep communities in the deepest parts of the trench, the biological picture would be dramatically different. Chemosynthetic communities have their own characteristic fauna, much of it distinct from the typical Hadal assemblage. There could be tube worm colonies, dense beds of chemosymbiotic clams, specialized bacterial mats, and a whole suite of associated organisms that would not show up in a trawl sample taken from a non-seep location. The possibility is not remote. It is in fact quite plausible given what we know about the geology. The Aleutian subduction zone is tectonically vigorous, seismically active, and has been driving fluid through its sediment column for tens of millions of years. The conditions for cold seep development are present. What is absent is the direct observation that would confirm or deny whether those conditions have produced the kind of chemosynthetic communities seen in comparable environments elsewhere around the Pacific. There is something almost frustrating about this, in a quiet way. Cold seep research is one of the more active areas of deep-sea biology right now. The communities around seeps are scientifically fascinating for a range of reasons, including their extreme longevity, their unusual biochemistry, their relevance to questions about the origins of life in chemically extreme environments, and their potential as analogues for life on other planets or moons where sunlight is absent, but chemical energy is available. Scientists are genuinely interested in finding and studying these communities, but the interest is not translated into expeditions to the deepest Aleutian Trench, because the logistical and financial barriers to getting there remain substantial, and because there are other cold seep sites that are easier to reach and already have established research programs. What makes this particularly interesting from a scientific standpoint is that Hadal cold seeps occurring below 6,000 metres, are almost completely unstudied. Most cold seep research has been conducted at continental margin depths, typically between a few hundred and a few thousand metres. The handful of observations suggesting seep-related activity in true Hadal environments, including some findings from the Aleutian Trench after the 2011 earthquake, represent the very edge of what has been documented. If the Aleutian Trench does harbour cold seep communities at Hadal depths, they would be among the deepest chemosynthetic ecosystems ever directly observed. That is not a minor scientific footnote. That would be a genuinely significant discovery. The chemistry of such a community would be worth studying carefully on its own terms. Deep subduction zone fluids carry a distinctive chemical signature, reflecting the minerals and organic material in the subducting plate as it is compressed and heated at depth. The methane produced in a subduction system can have a different isotopic character than methane produced by bacterial decomposition of organic matter in shallow sediment, and the organisms that metabolize it may have adapted to these specific chemical conditions in ways that differ from their counterparts at shallower seeps. Understanding the microbial communities at a Hadal subduction seep would add meaningfully to our picture of how life adapts to chemically extreme environments and how the deep carbon cycle operates in subduction zones. There is also a structural question worth considering. Cold seeps are not static features. They can be activated, intensified, or relocated by earthquakes, which alter the stress state of the sediment and can open or close fluid pathways. Given that the Aleutian Trench sits on one of the most seismically active subduction systems in the world, the relationship between earthquake activity and seep behaviour in this environment could be quite dynamic. An earthquake along the Aleutian system might trigger a pulse of fluid expulsion along the trench floor, temporarily intensifying seep activity and potentially affecting the biology of the surrounding area. Whether this happens, and on what timescale, is unknown, because the trench floor has never been monitored continuously or surveyed repeatedly over time in the way that would be needed to detect such changes. This is worth sitting with for a moment, because it illustrates something about how incomplete our picture of the deep ocean really is. We tend to think of the seafloor as stable and unchanging, at least on human timescales. But in a seismically active subduction zone, the floor of the trench may be considerably more dynamic than that. Sediment flows triggered by earthquakes can redistribute material across large areas. Fluid pathways can open and close. The chemistry of the sediment pore water can shift. The organisms living in and on the sediment must contend with these changes, and the communities that survive and thrive in this environment are presumably adapted to a degree of physical and chemical instability that most deep-sea organisms never experience. What that adaptation looks like in the Aleutian Hadal zone specifically, we simply do not know. The sediment itself, which was described earlier as a complicating factor for biological sampling, becomes relevant again here. The Aleutian Trench receives heavy sediment input from the Alaskan continental margin, and in some parts of the trench, the sediment layer is several kilometres thick. This sediment is not inert. It is a chemically active environment, hosting microbial communities that process organic material, produce methane through anaerobic decomposition, and interact with the fluids moving upward from the subducting plate below. The interface between the sediment column and the overlying water, and the interface between the sediment and the subducting plate beneath, are both zones of active chemistry and microbiology. Sampling either of these interfaces at Hadal depths in the Aleutian Trench has essentially not been done with modern equipment. There is a broader point here about how we categorise and think about Hadal environments. The scientific literature on Hadal trenches has tended to treat them primarily as extreme physical environments defined by depth, pressure, and cold temperature, and to focus on the organisms that have adapted to those physical extremes. The biological work has largely emphasised amphipods and other mobile scavengers, which are easy to trap and relatively easy to study. The chemical dimension of Hadal environments, particularly in subduction zone trenches where fluid expulsion and methane chemistry may be significant, has received much less attention. This is partly a function of the difficulty of chemical sampling at these depths, and partly a function of the fact that most Hadal research has been conducted in trenches where the subduction zone chemistry is less pronounced than it might be in the Aleutian system. If a well-equipped expedition were to reach the Hadal zone of the Aleutian Trench and find evidence of active cold seep communities, it would not just be a discovery about this one trench. It would prompt a re-examination of how we think about Hadal biology more broadly, and whether the standard picture of Hadal environments as food-limited, physically extreme but chemically unremarkable places is actually accurate for subduction zone trenches in general. That is a significant scientific implication for what might seem, from the outside, like a fairly narrow question about one understudied trench in the North Pacific. For now, the chemical and hydrothermal dimension of the Aleutian Trench remains largely in the realm of inference and possibility. The geochemical indicators are suggestive. The geological context is favourable. The analogues from other subduction zones are encouraging, but direct evidence from the Hadal zone itself is essentially absent, and the absence of evidence is not evidence of absence. It simply means that no one has yet looked carefully enough, in the right places with the right instruments. And that gap in knowledge sits alongside all the other gaps described in this story. The biological, the geological, the seismic, the chemical, each one reinforcing the others and collectively painting a picture of a place that is genuinely undercharacterized in ways that matter scientifically. What is perhaps most striking about the cold seep question is that it represents not just a missing piece of information, but a potentially missing category of life. There may be organisms living in the deepest Aleutian Trench that have never been seen, photographed, described, or named, not because they are rare or cryptic, but simply because no one has gone to look for them in the right way. And that is before we consider what else the trench might be holding, including a record of something far less natural and far more recent than chemosynthetic bacteria, something that arrived not from the geology below, but from the surface world above. That last thought is worth holding on to for a moment, because it shifts the frame of this story in a way that is quietly unsettling. Everything described so far has been about the trench as a natural system, the geology, the biology, the chemistry, the seismicity. All of it belongs to the Earth in some fundamental sense, even the parts that are difficult or dangerous or poorly understood. But there is another dimension to the Aleutian Trench that has nothing to do with geology or evolution, and it arrived much more recently than any of those processes. In 2017, a study published in Nature, Ecology and Evolution reported something that stopped a lot of people in their tracks. The researchers, led by Alan Jameson at Newcastle University, had collected amphipods from two of the deepest trenches in the world, the Mariana Trench and the Kermadec Trench, both reaching depths of around 10 to 11 kilometres. What they found in the tissue of those amphipods was not what most people would expect from animals living in some of the most remote and inaccessible environments on the planet. The amphipods contained persistent organic pollutants, PCBs and PBDEs, at concentrations that in some cases exceeded those found in crustaceans from heavily industrialized coastal rivers in China. Let that sit for a second. Animals living 7 to 10 kilometers below the surface of the ocean, in places that no human being has ever directly visited, were carrying industrial chemicals in their bodies at concentrations comparable to some of the most polluted nearshore environments on Earth. PCBs, polychlorinated biphenyls, were widely manufactured and used in electrical equipment and industrial applications through much of the 20th century. They were banned in the United States in 1979 and gradually phased out in other countries over the following decades, but they do not break down easily. They persist in the environment for a very long time, accumulating in fatty tissue and moving up through food chains. PBDEs, polybrominated diphenyl ethers, are flame retardants used in electronics, furniture and textiles, and they share similar properties. They are stable, they accumulate in fat, and they travel. The question, when you find them in deep-sea amphipods, is how they got there. The answer involves a combination of processes that, once you understand them, make a certain grim sense. Pollutants released into the ocean, whether from industrial discharge, atmospheric deposition, or the breakdown of plastic and other materials, attach to organic particles in the water column. These particles, dead plankton, fecal pellets, small fragments of organic matter, sink slowly through the water. This is sometimes called marine snow, and it is the primary food source for much of the deep-sea ecosystem. As it sinks, it carries whatever chemical compounds have attached to it, including persistent organic pollutants. In deep trenches, this material accumulates over time, because the geometry of a trench concentrates sinking particles from a wide surrounding area into a relatively narrow depression. The trench acts, in effect, like a funnel. Material that sinks from the surface across a broad region of ocean eventually ends up concentrated at the bottom of the trench, along with whatever pollutants it was carrying. Once the pollutants are in the sediment, they enter the food web through the organisms that feed on sediment and organic matter, and from there they move into the scavengers and predators that feed on those organisms. Amphipods, which are among the most abundant and ecologically important animals in Hadal trenches, feed on organic material that settles to the trench floor, including the carcasses of larger animals that sink from shallower depths. Because they are consuming material that has concentrated pollutants through the sinking process, and because the pollutants accumulate in fatty tissue rather than being excreted, the amphipods end up with surprisingly high concentrations of these compounds in their bodies. It is a straightforward process once you trace it through, but the result is still striking. The deepest parts of the ocean are not outside the reach of industrial pollution. They are in some ways sinks for it. The Aleutian Trench has not been directly sampled for persistent organic pollutants at Hadal depths, at least not in any study that has entered the public scientific record. But its position in the North Pacific makes it a particularly relevant case to think about. The North Pacific is one of the major ocean basins where persistent organic pollutants have accumulated over decades. Industrial activity along the Pacific Rim, including in the United States, Canada, Russia, Japan, China and South Korea, has introduced enormous quantities of these compounds into the atmosphere and ocean over the past century. Atmospheric transport carries pollutants across large distances, and deposition into the North Pacific has been documented extensively. The North Pacific Gyre, a large rotating system of ocean currents, tends to concentrate floating material in certain areas, but the underlying water column and sediment across the broader North Pacific have been shown to carry measurable pollutant loads. The Aleutian Trench sits along the northern edge of this system, receiving input from the Alaskan continental margin, which itself receives runoff and atmospheric deposition from a large geographic area. The trench is also positioned along one of the major shipping routes across the North Pacific, and shipping contributes to marine pollution through fuel combustion accidental spills and the gradual breakdown of materials. None of this means that the Aleutian Hadal zone is necessarily more polluted than the Mariana or Kermadec trenches, where the 2017 measurements were made, but it does mean that assuming the Aleutian Trench is somehow isolated from these pollution pathways would be naive. The geography simply does not support that assumption. There is also the matter of the heavy sediment input that has come up several times in this story. The Aleutian Trench receives sediment from the Alaskan continental margin at rates that are considerably higher than what is seen in mid-ocean trenches like the Mariana. Sediment is one of the primary carriers of persistent organic pollutants in marine environments because the organic matter in sediment particles provides attachment sites for hydrophobic compounds like PCBs. Higher sediment input, all else being equal, means a higher flux of pollutant-carrying material reaching the trench floor. This does not translate directly into higher tissue concentrations in organisms because many other factors are involved, but it does suggest that the Aleutian Trench sediment may carry a substantial chemical record of North Pacific pollution over the past several decades. What makes this particularly interesting from a scientific perspective is that deep-sea sediments are archives. The layers of sediment that accumulate in a trench record not just the biology and geology of the surrounding region, but also the chemical history of the overlying ocean. In principle, a sediment core from the Aleutian Hadal zone could contain a stratified record of pollutant deposition, going back through the 20th century, with higher concentrations in layers corresponding to the peak years of PCB production and use, and potentially declining concentrations in more recent layers following the bans and phase-outs of the 1970s and 1980s. This kind of chemical stratigraphy has been documented in other deep-sea sediment cores, and it provides a way of reconstructing the history of industrial pollution that is independent of the records kept by manufacturers or regulatory agencies. The trench floor, in other words, might be a more honest archive of what humanity released into the North Pacific than any industrial database. That is a sobering thought, and it is worth being clear about what it does and does not mean. It does not mean the Aleutian Trench is a wasteland, or that the organisms living there are dying from pollution, or that the ecosystem has been fundamentally destroyed by human activity. The amphipods sampled in the 2017 study were alive, they were functioning. The concentrations of pollutants in their tissue were high by comparison to clean environments, but the study did not establish that those concentrations were causing acute harm to the animals themselves. What the study did establish is that the assumption of pristine remoteness, the idea that the deepest parts of the ocean are somehow outside the reach of human industrial activity, is simply wrong. That assumption has shaped how we think about these environments, and it needs to be revised. For the Aleutian Trench specifically, the pollution dimension adds another layer to an already complicated picture. When scientists think about why this trench has been understudied, the conversation tends to focus on the practical obstacles, the weather, the seismicity, the engineering challenges, the funding gaps. Those are all real and significant, but the pollution question introduces a different kind of complexity. If the trench floor contains measurable concentrations of industrial chemicals, then biological samples taken from the Hadal zone carry a kind of inadvertent chemical record alongside their biological information. The amphipods you recover from a trap at 7,000 meters are not just specimens for taxonomic or ecological study. They're also chemical samples carrying information about the pollution history of the North Pacific in their tissue. That dual nature of the sample changes how you need to think about collection, storage, and analysis. It also changes the scientific narrative around what a future expedition to the Aleutian Hadal zone might actually find and document. The biological discoveries would be significant on their own terms, given how little modern biological data exists for this trench. But layered on top of that would be the chemical story, the question of what pollutants are present, at what concentrations, and what that tells us about how the North Pacific has absorbed and distributed the byproducts of a century of industrial activity. These two dimensions of inquiry, the biological and the chemical, are not separate. They are connected through the food web, through the sediment, through the sinking particles that link the surface ocean to the Hadal zone. There is something quietly strange about this when you think about it from the right angle. The Aleutian Trench is largely avoided because of its extreme conditions. The pressure, the weather, the seismicity, the engineering difficulty. It is treated in practical terms as one of the harder places on Earth to study. And yet, in another sense, the surface world has been reaching it continuously for decades, sending down its chemical residue through the slow rain of organic particles, depositing a record of industrial civilization in the sediment of a place that no human being has ever directly observed. The trench has not been isolated from us. We simply have not gone to look at what we have already sent there. This is not a comfortable thought, but it is not a reason for despair either. The 2017 study by Jameson and colleagues was not received as a catastrophe. It was received as a significant scientific finding that changed how researchers think about Hadal environments, and it prompted further work on pollutant distribution in the deep ocean. The same kind of reframing could apply to the Aleutian Trench if the right expedition were mounted with the right combination of biological, geological and chemical sampling objectives. The trench is not just a biological mystery or a geological puzzle. It is potentially a chemical archive of the North Pacific over the past century, and that archive is sitting at the bottom of 7,679 metres of cold water, largely untouched and unread. The question of what concentrations of persistent organic pollutants might be found in Aleutian Hadal amphipods if someone were to go and collect them is genuinely open. It is possible that the concentrations would be comparable to what was found in the Mariana and Kermadec trenches. It is possible they would be higher given the trench's position relative to North Pacific pollution pathways and its heavy sediment input. It is also possible that the picture would be more complicated, varying significantly along the length of the trench depending on local sediment dynamics, current patterns, and the distribution of organic matter input. The trench is 3,400 kilometres long after all, and conditions at its western end near Kamchatka are not the same as conditions at its eastern end near Attu Island. A single sampling point would give a snapshot but not a complete picture. What we can say with reasonable confidence is that the Aleutian Trench, like every other Hadal trench that has been sampled for persistent organic pollutants, is not chemically pristine. The North Pacific has been accumulating industrial chemicals for the better part of a century, and the trench sits at the bottom of that system, collecting what sinks. The organisms living there have been exposed to these compounds throughout their lives, and the sediment beneath them holds a layered record of how that exposure has changed over time. This is not speculation. It is an inference based on well-documented processes, applied to a place where the direct measurements have simply not yet been made, and that is perhaps the most honest summary of where things stand with the Aleutian Trench across nearly every dimension of inquiry covered in this story. The processes are understood. The mechanisms are documented elsewhere. The inferences are reasonable, but the direct measurements, the samples, the footage, the chemical analyses, the biological surveys with modern equipment, those are almost entirely absent. The trench is not unknown in the sense of being mysterious or legendary. It is unknown in the more mundane and frustrating sense of being a place where the work has not yet been done. Which brings the story, naturally, to a different kind of question. Not what is down there, but what it would take to actually find out, and whether the people and institutions with the tools to answer that question have any concrete plans to do so. There is another dimension to the Aleutian Trench that does not get discussed often in the context of deep-sea exploration, and it is one that connects this remote geological structure to something with very direct consequences for millions of people living around the Pacific Rim. The trench is not just a biological or chemical puzzle. It is also one of the most seismically significant features on Earth, and the degree to which scientists understand or do not understand its physical structure has real implications for how accurately we can model, predict, and respond to the earthquakes and tsunamis it generates. The Aleutian subduction zone is one of the most productive sources of large earthquakes anywhere on the planet. That is not an exaggeration for effect. The historical record, even just from the past century, is dense with major seismic events tied to the Pacific Plate's descent beneath the North American Plate along this boundary. The 1946 earthquake, the 1957 event, the 1964 Good Friday earthquake, the 1965 Rat Islands rupture. These are not isolated incidents. They are expressions of a system that is constantly accumulating and releasing stress, and they have collectively reshaped how the United States and other Pacific nations think about tsunami preparedness and early warning. The National Tsunami Warning Center, based in Palmer, Alaska, is the institution responsible for monitoring this system and issuing warnings when a seismic event has the potential to generate a destructive tsunami. It operates around the clock, drawing on a network of seismometers, ocean buoys, tide gauges, and satellite data to assess events in near real time. When a large earthquake occurs along the Aleutian subduction zone, the centre has a matter of minutes to determine whether a tsunami has been generated and how large it might be, and to issue warnings to coastal communities from Alaska to Hawaii to the west coast of the contiguous United States. The stakes of getting that assessment right are extremely high, and the speed at which it must be done is unforgiving. What makes this relevant to the trench specifically is that accurate tsunami modelling depends heavily on understanding the geometry and physical properties of the seafloor where the earthquake occurs. The shape of the rupture zone, the angle of the fault, the nature of the sediment overlying the plate boundary, the presence or absence of submarine landslides triggered by the shaking, all of these factors influence how a tsunami is generated and how it propagates across the ocean. And for the Aleutian Trench, many of these factors are poorly constrained because the trench floor itself has been so rarely surveyed. Tsunami modelling has become significantly more sophisticated in recent decades. Modern numerical models can simulate wave propagation across an entire ocean basin with reasonable accuracy, given good input data. The problem is that the input data for the Aleutian Trench remains coarser and less complete than for some other subduction zones. Bathymetric maps of the trench exist, but they are not uniformly high resolution along the entire 3,400 kilometre length. Sediment thickness and distribution data are available in parts of the trench, but not comprehensively. The mechanical properties of the sediment, how it behaves under the rapid loading of a major earthquake, are not well characterised for the Hadal portions of the trench. These are not trivial gaps. They translate into uncertainty in the models, and uncertainty in the models translates into uncertainty in the warnings. The 2021 Chignik earthquake, which occurred on July 28th of that year with a magnitude of 8.2, was a sharp reminder of how active this system remains. The earthquake struck near the Alaska Peninsula, close to the eastern end of the Aleutian subduction zone, and it was the largest earthquake recorded in the United States since the 2002 Denali earthquake. Tsunami warnings were issued for parts of Alaska, and coastal communities in the region were placed on alert. The tsunami that followed was real, but relatively modest in the areas that were warned, and the warnings were lifted within a few hours. From a public safety standpoint, the system worked, but the event also highlighted how quickly a large subduction zone earthquake can demand a response, and how much the quality of that response depends on the underlying scientific understanding of the fault system. What is interesting, and somewhat uncomfortable, is the gap that exists between the seismic monitoring infrastructure and the direct geological knowledge of the trench floor. The National Tsunami Warning Center has access to sophisticated monitoring networks and modelling tools. Seismologists have accumulated decades of data on how the Aleutian subduction zone behaves at the scale of the whole plate boundary, but the specific geometry of the trench at Hadal depths, the distribution and character of sediment at the base of the inner trench wall, the presence or absence of large-scale slope failures that could generate additional wave energy, these remain poorly known. The monitoring happens at the surface and in the water column. The floor of the trench, where the plate boundary is actually expressed as a physical feature, is largely unseen. This matters for a specific reason that is worth dwelling on for a moment. One of the more dangerous tsunami-generating mechanisms is not just the vertical displacement of the seafloor during an earthquake, but the triggering of large submarine landslides by that shaking. A submarine landslide can generate a tsunami that is locally much larger than the one produced by the earthquake itself, and because the landslide is a secondary event, it can sometimes produce wave heights that exceed what the seismic models predict based on the earthquake magnitude alone. The 1946 Aleutian earthquake is actually a case study in this phenomenon. The tsunami it generated was disproportionately large relative to its magnitude, and one leading explanation is that the earthquake triggered a significant submarine landslide along the trench wall, which added additional wave energy to what the tectonic rupture alone would have produced. The Scotch Cap Lighthouse on Unimak Island was destroyed by a wave estimated at around 35 metres, which is extraordinary for an earthquake of that size, and the discrepancy has been attributed in part to this kind of secondary mechanism. If that interpretation is correct, and most researchers who have studied the 1946 event consider it plausible, then understanding the susceptibility of the Aleutian Trench walls to landslide triggering is not just an academic geological question. It is a question with direct implications for tsunami hazard assessment. The inner walls of the trench, which are steep and heavily loaded with sediment derived from the Alaskan continental margin, may contain zones of weak or unstable material that could fail during a major earthquake. But without detailed surveys of those walls, without sediment cores and geophysical profiles from the deep portions of the trench, it is difficult to say where those zones might be, how large a failure they might produce, or what the wave consequences would be for coastal communities downslope. There is also the question of slow slip events and their relationship to the trench. Slow slip events, sometimes called silent earthquakes, are episodes of fault movement that release stress over days or weeks rather than seconds, and they do not produce the strong ground shaking of a conventional earthquake. They have been documented along several subduction zones, including parts of the Cascadia margin and the Japan Trench system. Whether they occur along the Aleutian subduction zone, and if so where and how frequently, is not fully established. Some researchers have suggested that the sediment-rich portions of the Aleutian subduction interface may be more prone to slow creep and slow slip behaviour than the sediment-poor portions, which could have implications for how stress is distributed and where future large ruptures might initiate. But again, the direct physical evidence from the trench floor that would help constrain these models is sparse. The Japan Trench offers a useful comparison here. Before the 2011 Tohoku earthquake and tsunami, the Japan Trench had been studied far more extensively than the Aleutian Trench, with multiple research cruises, sediment cores, and geophysical surveys. And yet the 2011 event still surprised the scientific community with the magnitude of the slip that occurred near the trench axis, which was much larger than most pre-event models had predicted. Part of the reason for that surprise was that the mechanical behaviour of the sediment at the shallowest part of the subduction zone, right at the trench, had not been adequately characterised. The integrated ocean drilling programme subsequently drilled into the Japan Trench fault zone as part of a rapid response effort, recovering sediment cores that helped explain why such large slip had occurred. That post-event drilling programme was scientifically valuable, but it was reactive. The knowledge it produced came after the disaster, not before. The lesson that some researchers have drawn from the Tohoku event is that understanding the physical properties of the trench floor and the shallow subduction interface is not a luxury or a purely academic exercise. It is part of the foundation of hazard assessment for the most destructive natural events that subduction zones produce. And by that standard, the Aleutian Trench represents a significant gap in the global inventory of well-characterised subduction systems. It is one of the longest and most seismically productive subduction zones on Earth, and the Hadal portion of its trench floor has never been the subject of a dedicated geological or geophysical survey with modern equipment. The bathymetric data that exists for the Aleutian Trench comes from a combination of ship-based multi-beam surveys, some of which are relatively recent, and older single-beam data that is considerably less detailed. The coverage is not uniform. Some sections of the trench have reasonably good modern bathymetry, while others are still represented primarily by older, lower-resolution data. The GEBCO Global Bathymetric Chart, which synthesizes available depth data from around the world, includes the Aleutian Trench, but the resolution in the Hadal portions is constrained by how much direct survey data actually exists. Gaps in the underlying data show up as smooth interpolated regions in the chart, areas where the model fills in what the measurements do not cover. For a feature as seismically significant as the Aleutian Trench, smooth interpolation in the bathymetry is not a reassuring thing to see. There have been some efforts to address the mapping gaps. NOAA and partner institutions have conducted multi-beam surveys along portions of the Aleutian Arc, and some of this data has improved the picture of the trench's outer slope and the shallower portions of its inner wall. The Alaska Ocean. Observing System and related programs have worked to build out monitoring infrastructure in the region. These are genuine contributions, and they have improved the scientific baseline. But they have not resolved the fundamental problem of the deep trench floor, the Hadal zone below 6,000 meters, which remains the least surveyed portion of the entire structure. There is something worth pausing on in this particular gap. The Aleutian Trench is not located in some impossibly remote corner of the ocean. It runs along the southern edge of United States territory, adjacent to the Alaska Peninsula and the Aleutian Islands, which are part of the state of Alaska. The United States has significant scientific infrastructure, a large oceanographic research fleet, and well-funded institutions with expertise in both deep-sea science and seismic hazard assessment. And yet the deepest part of this trench, which sits within or adjacent to US waters, and which is directly relevant to the tsunami hazard facing US coastal communities, remains largely unmapped and unsampled at Hadal depths. The reasons for this are the same ones that have come up throughout this story. The weather, the engineering challenges, the funding priorities, the logistical difficulty. But the combination of scientific importance and practical neglect is particularly stark when you frame it in terms of public safety, rather than pure scientific curiosity. It is worth being careful not to overstate the risk here. The National Tsunami Warning Center does function effectively, and it uses the best available data and models to issue warnings. The Aleutian subduction zone is not unmonitored. The gaps in knowledge of the trench floor do not mean that the warning system is broken or that communities are unprotected. What they mean is that the models underlying the warnings carry more uncertainty than they would if the trench floor were better characterized, and that uncertainty is concentrated in some of the most consequential scenarios, the very large earthquakes that produce the biggest tsunamis and that are most likely to involve complex rupture dynamics and secondary landslide triggering. Scientists who work on subduction zone hazards are generally aware of these gaps. The Aleutian Trench appears in hazard assessment literature, in discussions of potential future great earthquakes, and in planning documents for tsunami preparedness. The scientific community has not ignored this system. But awareness of a gap and the resources to close it are different things, and the specific combination of deep geological and geophysical work that would most directly address the uncertainty, surveys of the Hadal Trench floor with high-resolution equipment, sediment coring at depth, characterization of the shallow subduction interface near the trench axis, has not been the subject of a dedicated, well-funded campaign in the way that some other subduction zones have been studied. The 2011 Tohoku disaster prompted a significant increase in scientific attention to the Japan Trench and to the general question of how subduction zone trenches behave during great earthquakes. Whether a comparable event along the Aleutian subduction zone would prompt a similar response is an uncomfortable thing to think about, because it implies waiting for a catastrophe to motivate the science that might have helped anticipate it. The better outcome, obviously, would be for the scientific and funding communities to treat the Aleutian Trench as the high-priority research target that its seismic history and public safety relevance suggest it should be, before the next major event rather than after. That is the tension that runs through the seismic and tsunami dimension of this story. The trench is important, measurably and demonstrably important, in ways that go beyond scientific curiosity and reach into the practical domain of hazard assessment and community safety. The knowledge gaps are real, and they have real consequences for the accuracy of the models that warning systems depend on. And yet the work that would close those gaps has not been done, for reasons that are frustratingly mundane: weather, cost, logistics, competing priorities, the gravitational pull of better studied places. Which makes it worth asking, finally, what it would actually take to change that picture. What does a realistic modern effort to study the Aleutian Islands zone look like, and is anyone actually planning one? So let us actually look at what that realistic picture might involve, and where things stand right now. The honest starting point is that the tools capable of reaching the Hadal zone of the Aleutian Trench do exist. They are rare, expensive, and in high demand, but they are real. Full ocean depth vehicles, meaning systems rated to 11,000 meters or more, have been built and operated successfully. The question is not whether the technology is theoretically possible. The question is whether the specific combination of the right equipment, the right funding, the right institutional partners and the right weather window has ever been assembled with the Aleutian Trench as the specific target. And the answer, as of the early 2020s, is that it has not. To understand why that matters, it helps to look at what the closest comparable efforts have actually looked like. The Five Deeps expedition, which ran from 2018 into 2019, was in many ways the most ambitious trench diving program in the modern era. Funded privately by Victor Vescovo, a retired naval officer and accomplished mountaineer, the expedition used the DSSV pressure drop as its surface vessel and the DSV limiting factor as its dive vehicle. The limiting factor is a two-person submersible built by Triton submarines and rated to full ocean depth. Over the course of the expedition, Vescovo and a rotating team of scientists dove to the deepest point of each of the 5 oceans: the Puerto Rico Trench in the Atlantic, the South Sandwich Trench in the Southern Ocean, the Java Trench in the Indian Ocean, the Molloy Deep in the Arctic, and the Challenger Deep in the Pacific. The Challenger Deep dive, completed in April 2019, reached approximately 10,928 meters, setting a new record for the deepest crewed descent. What the Five Deeps expedition demonstrated, among other things, was that full ocean depth exploration is operationally feasible with modern equipment and sufficient resources. The limiting factor performed reliably across multiple extreme dives. The science that came out of the expedition, conducted in partnership with researchers from institutions including WHOI and Newcastle University, included new bathymetric data, biological samples, and lander deployments that collected footage and specimens from Hadal depth that had rarely or never been directly observed. The expedition was not without its logistical difficulties, and not every dive went exactly as planned, but the overall program succeeded in doing something that had never been done before, reaching the deepest point of every ocean in a single coordinated effort. The Aleutian Trench was not part of that program. The Five Deeps focused on the single deepest point of each ocean, and the deepest point of the Pacific is the Challenger Deep in the Mariana Trench, not the Aleutian. But the expedition is relevant here because it established a template for what modern Hadal exploration looks like when resources and commitment are actually in place. The limiting factor, operated through the Inkfish organisation that grew out of the Five Deeps program, has continued to conduct deep dives in various locations. The question is whether the Aleutian Trench will eventually appear on that list. For most of the scientific community, the more realistic near-term pathway involves not crewed submersibles, but autonomous and free-falling lander systems. Landers are, in simple terms, weighted frames carrying instruments and cameras that are dropped from a ship, sink to the bottom under their own weight, collect data and samples for a set period, and then release their ballast weights and float back to the surface. They have no tether connecting them to the ship during the dive, which removes one of the major risks associated with deep operations in rough conditions: cable management. In a place like the Aleutian region, where surface conditions can deteriorate rapidly, and where a tether connecting a ship to something 7 kilometers below the surface would be under constant mechanical stress from wave action and ship movement, the lander approach has real advantages. Landers have been used successfully in a number of Hadal trenches, including the Mariana, Kermadec and Japan trenches. Alan Jameson at Newcastle University, who's been one of the most productive researchers in Hadal biology over the past 2 decades, has used lander systems extensively. His work and that of his collaborators has produced much of the modern biological data from Hadal depths, including the 2017 pollutant study and numerous papers on amphipod distribution and behaviour. The lander approach is not without its own challenges. The systems have to be rated to full depth. The acoustic release mechanisms that drop the ballast weights have to function reliably after hours at extreme pressure, and there is always some risk that the lander will not return. But compared to the operational complexity of deploying an ROV or crewed submersible from a ship in difficult conditions, landers are relatively tractable. An array of landers deployed across multiple points along the Aleutian Hadal zone could, in principle, provide biological samples, sediment samples, and video footage from depths that have not been directly observed since the Soviet-era trawl expeditions of the 1950s and 1960s. The data would be fragmentary compared to what an ROV survey could produce, but it would be a genuine start. And the logistical footprint of a lander-based expedition is smaller than a full ROV program, which means the weather window required for safe operations, while still narrow, is somewhat more achievable. The Schmidt Ocean Institute, based in Palo Alto and operating the research vessel Falkor and later the larger Falkor 2, has been one of the more active organisations in terms of making deep-sea research accessible to scientists who might not otherwise have access to ship time. Their primary deep-sea vehicle is the ROV Sebastian, which is a capable and well-instrumented system. Sebastian is rated to 4,500 metres. That depth rating covers a large portion of the global ocean floor, and it is sufficient for a great deal of scientifically important work. But it falls short of the Aleutian Hadal zone by more than 3 kilometres. A Sebastian expedition to the Aleutian Trench could survey the upper walls of the trench, the transition into the Hadal zone, and the biological communities living at mid-trench depths, and that work would be genuinely valuable. But it could not reach the floor of the deepest portions, which is precisely where the most scientifically distinctive conditions exist. This is a recurring problem in Hadal research more broadly. Most of the world's research, ROVs, are rated to 6,000 metres or less. That depth limit is not arbitrary. It reflects a practical engineering and economic calculation. The pressure at 6,000 metres is already around 600 atmospheres, and building systems that can handle that reliably is already technically demanding and expensive. Pushing to 7,000 metres or beyond requires a step change in engineering, not just incremental improvement, and that step change carries a significant cost premium. For institutions operating on research budgets, the additional capability has to be weighed against everything else that money could do. The vehicles that are rated to full ocean depth are few. The DSV limiting factor is 1. The Chinese submersible Fenduji, which set a new record for the Challenger Deep in 2020 at approximately 10,909 metres, is another. Japan's Jamstek has operated the crewed submersible Shinkai 6,500, which as its name suggests is rated to 6,500 metres, deep enough to reach the Aleutian Hadal zone, but not by a comfortable margin. Jamstek also operates lander systems and has been involved in Hadal research in the Japan Trench and elsewhere. Whether Jamstek or a comparable institution might eventually turn attention to the Aleutian Trench is an open question, and not an entirely unlikely one given the seismic and biological parallels between the two subduction systems. There's also the question of autonomous underwater vehicles, or AUVs. These are untethered robotic systems that can be programmed to follow a survey path, collecting data as they go, and then return to a recovery point. AUVs have been used extensively for midwater and seafloor mapping, and some systems are rated to significant depths. The WHOI vehicle Nereus, before its loss in the Kermadec Trench in 2014, was a hybrid system that could operate either as a tethered ROV or as a fully autonomous AUV, and it was rated to full ocean depth. Its loss was a significant setback for the Hadal research community, partly because of the scientific capabilities it represented, and partly because it demonstrated concretely the risk that extreme pressure poses even to carefully engineered systems. The implosion that most likely destroyed Nereus was not the result of a design flaw in any simple sense. It was a consequence of operating at a pressure regime where the margin for error is very small, and where the consequences of any failure are immediate and total. Since Nereus, WHOI and other institutions have been working on next-generation deep vehicles, but the pace of development is slow relative to the scientific need, and the funding environment for major capital equipment in oceanography is competitive. The National Science Foundation, which funds much of the US oceanographic research fleet and its associated equipment, has to balance requests for deep capable vehicles against a long list of other priorities. The result is that the community of researchers who want to work in Hadal environments is consistently larger than the available vehicle time to support them. It is worth noting that there has been some relevant technological development on the lower cost end of the spectrum. Newer lander designs have become more modular and somewhat less expensive than earlier systems, making it more feasible for smaller research groups to build or acquire them. There is also growing interest in using gliders and other long-endurance autonomous platforms for water column work in the trench environment, which could provide data on the biological and chemical structure of the water above the Hadal zone, even if it cannot directly sample the floor. None of this replaces the need for a full-depth lander or vehicle program, but it represents a gradual lowering of the barrier to entry for some kinds of Aleutian Trench research. The Hades program, the NSF-funded Hadal Ecosystem Studies project that ran from around 2012 and produced much of the modern scientific literature on Hadal biology and chemistry, focused its efforts primarily on the Mariana Trench, with some work in the Kermadec and Tonga trenches as well. The Aleutian Trench was not a target. The reasons were largely the ones that have come up throughout this story: logistics, weather, the availability of existing infrastructure near the Mariana, and the accumulated momentum of prior research in those locations. The Hades program was genuinely productive and advanced the field considerably, but its geographic focus meant that the Aleutian Trench continued to accumulate scientific debt, while other trenches were being studied in detail. As of the early 2020s, there is no publicly announced expedition specifically targeting the Hadal zone of the Aleutian Trench with full-depth capable equipment. That does not mean nothing is being planned. Scientific expeditions often take years to develop from initial concept to funded, permitted and operational programs, and not all planning activity is publicly visible at early stages. It is possible that somewhere in the overlapping networks of Hadal researchers, funding agencies and research vessel operators, conversations about the Aleutian Trench are happening. What is clear is that nothing has yet reached the stage of a confirmed, funded program with a specific deployment date. What would it actually take to change that? The honest answer is probably a combination of factors rather than any single one. A dedicated funding call from NSF or NOAA specifically targeting the Aleutian subduction system, framed around both the biological and the seismic hazard dimensions, would help. Access to a full-depth capable vehicle through a partnership with a private operator like Inkfish, or through a bilateral arrangement with Jamstec would be necessary. A research vessel capable of operating in North Pacific conditions, which rules out some of the smaller or less ice-capable ships in the research fleet, would need to be scheduled during one of the narrow weather windows when the Aleutian region is manageable, and a team of scientists willing to commit to the logistical difficulty and the inherent uncertainty of working in one of the most operationally challenging ocean environments on Earth would need to be assembled. None of those requirements is individually impossible, The difficulty is in getting all of them to align at the same time, which is harder than it sounds in a research funding and planning environment, where every element has its own timeline, its own institutional dependencies and its own competing demands. The Mariana Trench got its modern wave of attention partly because of its depth record, which gave it a kind of cultural and scientific prestige that attracted both funding and private interest. The Aleutian Trench does not have that particular draw. It is not the deepest, it is not in a convenient location, it does not have a famous name attached to it the way the Challenger Deep does. What it has is scientific importance, which is real and substantial, but which has not yet been sufficient to overcome the practical barriers. That gap between importance and attention is, in a way, the most interesting thing about the Aleutian Trench's current situation. It is not overlooked because it is unimportant. It is overlooked because the system of scientific planning and resource allocation consistently finds reasons to go elsewhere, and because the specific combination of factors that would make a dedicated Hadal expedition feasible has not yet come together. The trench sits there, 7.5 kilometres deep in one of the stormiest stretches of ocean in the world, accumulating sediment and seismic events and biological time, waiting for the moment when the science and the resources finally converge. Whether that moment comes soon, or whether it waits for some future generation of researchers with better tools and different institutional priorities, is genuinely unclear. What is clear is that the question of what lives and moves and accumulates in the deepest parts of the Aleutian Trench remains, for now, largely unanswered, and the answers, when they eventually come, are likely to be worth the wait. So let us sit with that for a moment, because there is something worth naming plainly before we move toward the end of this story. The Aleutian Trench is not obscure because it is unimportant. It is not understudied because scientists looked at it and decided there was nothing there. It is not avoided because of some institutional conspiracy or deliberate neglect. The situation is both simpler and more interesting than any of those explanations. It is a place that has been consistently, systematically, and almost inevitably deprioritized by the ordinary logic of how science gets funded, how expeditions get planned, and how research attention flows toward places that already have some prior investment and some existing infrastructure to build on. The Aleutian Trench has been left behind not by dramatic decision but by accumulated inertia, by the quiet accumulation of practical reasons to go somewhere else. That is worth understanding clearly, because it changes how we think about what the trench represents. When we talk about unexplored places, there is a temptation to reach for the language of mystery, to make the unknown sound like something hidden by design, something that has been kept from us, something that waits in the dark like a secret. The Aleutian Trench is not like that. Its obscurity is not romantic in that way. It is the result of weather patterns and funding cycles, and the physics of deep-sea engineering and the geography of research port infrastructure. It is the result of the fact that the Mariana Trench has better weather and a more famous name and decades of prior research that made each subsequent expedition easier to justify and fund. The Aleutian Trench's situation is, in a way, more honest than a mystery. It is just a very hard place to get to, in a very expensive kind of science, in a funding environment that rewards momentum and penalizes novelty. And yet, the things we do not know about it are genuinely significant. We do not know what lies in the deepest parts of the trench right now, in 2024 or 2025, with any degree of modern biological resolution. The Soviet trawl samples from the 1950s and 1960s told us that amphipods and polychaetes and holothurians can survive at those depths, which is useful information, but it is the kind of information that tells you a community exists without telling you anything about how it is structured, how dense it is, how it varies across the length of the trench, what it is eating, how it reproduces, or how it has changed over the decades since those samples were taken. Modern Hadal biology has moved far beyond what a trawl sample can reveal. High-resolution video, in situ chemical sensors, carefully preserved tissue samples for genetic analysis, baited traps with time-lapse cameras, sediment cores taken from specific microhabitats. All of these tools have transformed what we understand about life in other trenches. None of them have been applied to the Aleutian Hadal zone in any systematic way. We do not know whether there are cold seep communities in the deepest parts of the trench. The geochemical signals are consistent with fluid expulsion from the subducting plate. The geology is the right kind of geology. Other subduction trenches, the Japan Trench, the Cascadia Margin, the Hikurangi Trough off New Zealand, have documented cold seep ecosystems with chemosynthetic bacteria, tube worms, clams adapted to sulfide-rich sediment, and a whole food web built on chemical energy rather than sunlight. There is no particular reason to think the Aleutian subduction zone is exempt from these processes, but we have not looked, and so the question of whether there are chemosynthetic communities in the Aleutian Hadal zone is not answered. It is just open. We do not know what the sediment record at the bottom of the trench contains. Sediment cores from Hadal trenches have turned out to be remarkable archives, recording earthquake events as turbidite layers, preserving organic material from the surface ocean going back thousands of years, and, more recently, recording the chemical signature of industrial pollution. The 2017 study that found PCBs and PBDEs in amphipods from the Mariana and Kermadec trenches was a significant scientific moment, not because it was surprising in retrospect, but because it made viscerally clear that the deepest parts of the ocean are connected to the surface world in ways that matter. The Aleutian Trench sits in the North Pacific, downstream of major pollution pathways, in a region where surface productivity is high and particle sinking is substantial. If any trench in the world is accumulating a detailed chemical record of North Pacific industrial history in its sediment, the Aleutian Trench is a strong candidate. But again, no one has taken a core from the Hadal zone to check. And then there is the seismic dimension, which is perhaps the most practically urgent of all the open questions. The Aleutian subduction zone is one of the most seismically active convergent margins on Earth. The 1946 earthquake and the tsunami that killed 159 people and erased the Scotch Cap Lighthouse, the 1957 and 1965 events, the 1964 Good Friday earthquake, the second largest ever recorded, which reshaped entire coastlines and sent waves across the Pacific. The 2021 Chignik earthquake, a reminder that the system has not quieted down. All of these events originate in or near the same geological structure whose floor we have never properly mapped. The geometry of the trench floor, the structure of the sediment layers, the location and character of the fault surfaces within the subduction zone, all of this is directly relevant to understanding how earthquakes nucleate and propagate in this system, and therefore directly relevant to the quality of the tsunami warnings that protect coastal communities from Alaska to Hawaii to Japan. The National Tsunami Warning Center does its work with the data it has, but the data it has is incomplete in ways that matter, and some of what is missing could only be filled in by direct investigation of the trench floor itself. That combination of unknowns, biological, chemical, geological, seismic, is what makes the trench's continued neglect feel genuinely significant rather than merely interesting. It is not just that there are fascinating creatures we have not yet catalogued. It is that the trench holds information relevant to ecosystems, to pollution history, to public safety, and to our basic understanding of how the Pacific Rim functions as a geological system. The gap between what we could know and what we actually know is not a small one. There is a broader pattern here that the Aleutian Trench illustrates quite well. The ocean covers about 71% of the Earth's surface, and the deep ocean, below 200 metres, makes up the vast majority of the biosphere by volume. We have mapped less of the ocean floor in high resolution than we have mapped the surface of Mars. The Hadal zone, everything below 6,000 metres, is the least explored part of the deep ocean, and within the Hadal zone, the trenches that are well studied, the Mariana, the Kermadec, the Tonga, are a small and somewhat arbitrarily selected subset. The Aleutian Trench is not unique in being understudied. It is part of a much larger pattern of ocean science, operating with a tiny fraction of the resources needed to actually understand the environment it is trying to describe. But the Aleutian Trench is a particularly clear example of the pattern, because the gap between its scientific importance and its scientific attention is so large, and because the reasons for that gap are so plainly practical rather than principled. Nobody decided the Aleutian Trench was unimportant. The system just consistently found reasons to go elsewhere. What might change that? It is worth thinking about, not as a prediction, but as a way of understanding what the actual barriers are. One possibility is a seismic event, a major earthquake in the Aleutian system, particularly one that generates a damaging tsunami, tends to focus scientific and governmental attention on the subduction zone in ways that can translate into funding for research. After the 2004 Indian Ocean earthquake and tsunami, there was a significant increase in funding for subduction zone research globally, and for tsunami warning infrastructure specifically. A similar event in the Aleutian system could generate the political and institutional will to fund a proper geological survey of the trench floor, which would almost certainly include some Hadal sampling as a component. That is not a reason to wish for such an event. It is just an observation about how scientific funding sometimes responds to catastrophe more readily than to quiet importance. Another possibility is private sector interest. The 5 Deeps expedition, which used the DSV limiting factor to reach the deepest point of each of the world's 5 oceans, was funded by Victor Vescovo, a private investor and explorer. That expedition produced genuine scientific data and demonstrated that a single, motivated individual with sufficient resources could accomplish what government science programs had not managed to prioritize. A similar private initiative focused on the Aleutian Hadal zone is conceivable. The scientific community would need to be involved to ensure the work was done rigorously, but the model exists. Inkfish, the organization that now operates the limiting factor, has continued doing deep science work in various locations. Whether the Aleutian Trench becomes a target for that kind of initiative is an open question. A third possibility is simply the slow accumulation of scientific momentum. As lander technology becomes cheaper and more modular, as autonomous underwater vehicles improve their endurance and depth ratings, as the general infrastructure of Hadal science matures, the barrier to doing at least some work in the Aleutian Trench gradually lowers. It may not take a single dramatic expedition to begin filling in the picture. It may happen incrementally through a series of smaller deployments, water column surveys, lander drops from ships transiting the area for other purposes, collaborative sampling during seismic monitoring cruises. The picture that emerges might be assembled piece by piece over a decade rather than revealed all at once by a single major program. Any of those paths would be welcome. All of them remain uncertain. For now, the trench is what it has been for the duration of this story. A 7.5 kilometre deep structure running for 3,400 kilometres along one of the most tectonically active margins on Earth, largely unmapped at its deepest levels, biologically uncharacterised in any modern sense, chemically unsampled at Hadal depths, and seismically monitored from the surface without any direct knowledge of the geological structure it is monitoring. It is a place that the science of the 21st century has the tools to study, but has not yet found the combination of will, resources, and logistical alignment to actually reach. There is something quietly humbling about that. We live in a period when we can sequence the genome of an organism from a few cells, when we can image a black hole 47 million light-years away, when we can land a rover on Mars with enough precision to target a specific ancient river delta. And yet the bottom of a trench in the North Pacific, 7.5 kilometres below the surface of our own ocean, on our own planet, remains largely unknown. Not because we lack the technology, not because the science is impossible, but because the practical barriers are high enough and the competing demands on scientific resources are numerous enough that the specific combination required to go there and look has not yet come together. That is not a failure of science. Science is doing what it can with what it has, and what it has is never enough to study everything that deserves study. It is more of a reminder that the map of human knowledge is shaped not just by what is possible, but by what is funded, what is logistically feasible, and what has accumulated enough prior momentum to attract the next wave of attention. The Aleutian Trench is waiting at the edge of that map, not quite reached, not quite known. What is down there, in those specific few square kilometres near Aleutian Island where the depth reaches its maximum, is genuinely uncertain. There are almost certainly amphipods. There are almost certainly other Hadal invertebrates adapted to the pressure and the cold and the particular chemical character of that sediment. There may be cold seep communities built around chemosynthetic bacteria, thriving in complete independence from sunlight. There is almost certainly a sediment record that would tell us something important about the earthquake history of the region and the pollution history of the North Pacific. There may be things that do not fit neatly into any of those categories. Things that a camera lowered to that depth for the first time would reveal that we are not currently expecting, because that is what tends to happen when you actually go and look at a place no one has looked at carefully before. The deep ocean has a long history of surprising the people who study it. The discovery of hydrothermal vents in 1977 was genuinely unexpected. The density of amphipod populations in the Challenger Deep surprised researchers who assumed the deepest environments would be nearly barren. The pollution concentrations found in Hadal amphipods in 2017 were, to many people, startling, even though the mechanisms that produced them were entirely logical in retrospect. The Aleutian Trench is the kind of place that seems likely to produce its own version of that experience whenever someone finally goes there with the right equipment and enough time to look carefully. That moment has not arrived yet, but the trench is patient. It has been there for 50 million years, give or take, and it will be there when the funding and the logistics and the institutional will finally align. The sediment will still be accumulating. The amphipods will still be going about whatever it is amphipods do at 770 atmospheres of pressure in the dark. The fault surfaces will still be locked and slowly building strain. The cold, still water at the bottom will still be holding whatever chemical record it has been quietly assembling for decades. And somewhere, probably, a researcher is writing a proposal, or sketching out a cruise plan, or talking to a program manager about whether the timing might finally be right to do this properly. The gap between that conversation and an actual expedition is real, but it is not infinite. If you have been listening to this tonight, wherever you are, whatever the hour, thank you for spending this time with a place that most people have never thought about and that even most scientists have never directly studied. The Aleutian Trench does not have a famous name. It does not have dramatic footage attached to it. It does not have a well-known discovery story. What it has is depth and age and scientific importance and a long list of open questions that are genuinely worth answering. That feels like enough to be worth an evening's attention. If this story stayed with you, if you found yourself thinking about what sits at the bottom of that long cold scar in the North Pacific, consider leaving a like or subscribing so you find your way back here when there is more to talk about. It genuinely helps this channel keep going, and it means a great deal. This has been Life Beyond Seen. Rest well, wherever you are.